Test. 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 All right, I think it's working. All right, everybody, welcome to another Hoopo stream. This is the last stream this week, so we're going to close it off with something a little bit interesting here. This is called Bayesian flow networks. So the reason this is popular is because of this guy, Alex Graves. So Graves, this one, computer scientist. So this is a guy who was one of the original Schmidt-Huber students, I guess. PhD under Schmidt-Huber, who's kind of his own character within the deep learning world, and has kind of worked all over the place, it seems. Worked at Google, worked at DeepMind, and now seemingly works at NNAI Sense, whatever the fuck that is. This is some kind of like, what is this exactly? I don't exactly know. Mission? Large-scale neural network solutions for industrial process inspection. Outgrow of the Swiss AI Institute. So, I don't know. Hard to know exactly what that is, but Alex Graves himself is famous for his previous work, including neural Turing machines, differentiable learning computer, and then also the LSTM. So he's someone who has a history of kind of finding new and intuitive ways to do machine learning in a different way. And that's why this paper is popular. But with that said, let's go ahead and see if it deserves the hype. This paper introduces Bayesian flow networks, a new class of generative models, so a model that can generate new things. In this case, it's going to be generating, I guess, samples from some kind of a distribution, in which the parameters of a set of an independent distribution, so distributions like the normal distribution, and then the parameters of that distribution would be things like the mean and the variance. So a bunch of means and a bunch of variances for a bunch of normal distributions would fit under this definition. Are modified with Bayesian inference in the light of noisy data samples. So your data has some noise in it, and then passed as input to a neural net that outputs a second interdependent distribution. So a distribution that is dependent on the data samples. I don't know. We're going to see exactly what they mean here. Starting from a simple prior, so a prior is kind of your belief about the distribution and the world before you partake in this statistical modeling quest. So a simple prior might be something like a Gaussian. That's probably what it is. It's probably a normal prior. That's a very common prior. And then iteratively updating the two distributions yields a generative procedure similar to the reverse process of a diffusion model. Okay, so the diffusion model here, maybe the noise is being added, right? Diffusion models, you're adding and removing noise and then learning the structure of the data by doing that adding and removing of noise. So there's probably maybe something similar happening here where you're adding and removing noise to the data, and in that way finding the true underlying structure of that data. How's it going, Luke? However, this is conceptually similar in that no forward process is required. Okay, conceptually simpler, sorry. Discrete and continuous time loss functions are derived for continuous and discretized. So the time in a diffusion model is discretized, right? You're removing noise, but it's at a set of discrete steps. So it seems like they probably have a similar thing here. They have discrete loss functions, but also a continuous loss function. Discretize and discrete data along with sample generation procedures. Notably, the network inputs for the discrete data lie on the probability simplex. What? So Let's look that up. Probability simplex. A probability simplex is a mathematical space where each point represents a probability distribution between a finite number of mutually exclusive events. Okay, so let's say, I guess here, you have something that can either be this top corner of the triangle, the bottom corner of the triangle, or this corner of the triangle. And each of these corners represent some situation, right? And if you're here, then it's 100% you're in here. If you're here, it's 100% you're here. 0 simplex, 1 simplex. So a coin flip is a 1 simplex, right? It can only be either heads or tails, and the probability is somewhere in between there, depending on whether your coin is biased towards head or biased towards tails. A 2 simplex, here you have 3 possible outcomes, but I think the main intuition that you want here is that it's a space where each point represents a probability distribution between a finite number of mutually exclusive, keyword there, exclusive, where it has to be one of those things, but the probability distribution has to sum to 1, so you have to have something has to happen, right? At the end, the probability is 1 of something happening. Okay, but already not starting off in necessarily a good way here with these overly mathematical terms. There are therefore natively differentiable. Okay, I guess simplex is differentiable because it's just a line or a point in a triangle or a point in a, what is this, a pyramid, triangle, tetrahedron. Okay. Paving the way for gradient-based sample guidance. Okay, so if you can differentiate your thing, you can do gradient descent in order to improve the thing. And few-step generation in discrete domains such as language modeling. So language modeling the next token, right? Predicting the next token is a form of modeling language. You're trying to create a statistical model of what language is such that you can, given the first part of a sentence, predicts the probability distribution of the next token in the sentence, right? And that's discrete because there's a limited amount of tokens. There's only, 26 letters, and then a limited amount of combination of those letters that makes sense in English. And then you can make that a little bit wider if you want to include all the other languages and ASCII characters. The loss function directly optimizes data compression. This is pretty good because I did post this on the Discord, but actually just recently, Ilya Sutskever, who's like one of the OpenAI founders, released a talk where he talks about how basically generalization is compression, intelligence is compression. This is an idea that kind of goes back way further than that, but optimizing data compression seems like a very good kind of starting place if you're trying to build a generic kind of machine learning process and an algorithm, which is what this entire paper is about, right? It's about a new kind of neural network called a Bayesian flow network, which hopefully is better, I guess, than the current set of neural networks. Places no restrictions on the network architecture. Okay, so you can have lots of different types of Bayesian flow networks, I guess. In our experiments, Bayesian flow networks achieve competitive log likelihoods for image modeling on dynamically binarized MNIST and CIFAR10. So MNIST and CIFAR10 are pretty simple data sets. These aren't very complicated. Unfortunately, that kind of sets the tone for this paper. They're not going to be doing any state-of-the-art results or anything interesting. You're going to be looking at MNIST, which is these little digits. If you guys have ever seen MNIST, probably have, but they're very tiny little images of digits. They're just 28 pixels by 28 pixels, and they're basically one channel, right? Grayscale. CIFAR10 is the slightly harder version of that, which is now 3-channel. And rather than, this is CIFAR10. So they're 32 by 32, so a little bit bigger. And then they're also color, so whereas MNIST is one channel, just grayscale. CFAR is color, which means there's R, G, and B channels, three channels. And the classification is also bigger, right? So in MNIST, you just have 10 categories. It's 0 to 1 or 0 to 9. And in CFAR 10, you have a little bit more, or 10 classes. I guess maybe not. Maybe it's the same amount of classes. I thought there was more classes in CFAR 10, but maybe not. That makes a lot of sense why it's called CFAR 10 now. All right. And outperform all known discrete diffusion models on the text 8 character level language modeling task. So a discrete diffusion model would be something like a stable diffusion, right? Stable diffusion is discretized into these steps. I think pretty much all image diffusion models that we use nowadays are discrete. And I don't know what this text 8 character language modeling task is, but it's probably some simplified version of language modeling. So not next token prediction, but some constrained form of that where maybe you're trying to, I don't know, what is this? Rather than postulating, let me character text 8 benchmark. So the text 8 benchmark, currently the state of the art is GPT-2. It seems like it's lower is better. Can I understand more about this? What is this? Homepage. Holy shit, dude. Of course the text 8 benchmark would have a plain text website. This is very fitting. The text data for the large text compression is the first 10 to the 9th bytes of the English Wikipedia dump on 2006. Okay. So text 8 is, I guess, predicting the next character in a huge chunk of the Wikipedia from 2006. So that's the benchmark that they're going to be using for their language modeling. Good to know. All right, so this paper is obviously very recent, and it's been kind of getting more and more popular, and it was recommended by one of our viewers, so I figured we'd give it a try. Introduction. Large-scale neural networks have revolutionized generative modeling over the last few years with an unprecedented ability to capture complex relationships among many variables. Building a convincing joint model of all the pixels in a high-resolution image, for example, was impossible before the advent of modern generative networks. Was it really the advent of modern generative networks, or was it the creation of really large compute, like graphics processing units? I would say that that was really the difference maker there. I don't think the actual algorithms behind the generative networks that we use today are that important. I wonder if there'll be more or less Googling than the quantum attention paper. Probably a little bit less, but maybe not. We'll see. Key to the expressive power of most of these networks, including autoregressive models, flow-based models, deep VAEs, or variational autoencoders, and diffusion models, is that the joint distribution they encode is broken down into a series of steps. So a joint distribution is a distribution where there's multiple variables. So I think here the distribution they're talking about is that, for example, in a diffusion model, you have the distribution of the image, but then you also have the distribution of the image conditioned on some text, right? And you're trying to model that joint distribution, thereby eluding the curse of dimensionality that would doom any effort to explicitly define all the interactions among so many variables. In colloquial terms, they solve a hard problem by splitting it into pieces. Okay, so kind of here they're suggesting that this discretization of time is kind of fundamental, right? Breaking it down into a series of steps. So, I don't know, they're kind of setting the stage that maybe this breaking it down into a series of steps is what's wrong with all of machine learning, and if we don't have to do that, maybe we get to a better solution here. A general way to view such distributions is as an exchange of messages between a sender and her friend Bob, who wishes to receive it in as few bits as possible. I think these are the names of the people in the original Turing machine paper. I've seen those names before. I don't recall exactly where, but those are definitely some Easter egg reference to an earlier information theory paper. At each step, Alice sends a message to Bob that reveals something about the data. So you have Bob is trying to model some distribution and is receiving pieces of data one at a time. Bob attempts to guess what the message is. The better his guess is, the fewer bits are needed to transmit it. So this is the idea of once you have a very strong prior that is supported by a bunch of your data, you don't need as much data anymore to be convinced that your prior is good. After receiving the message, Bob uses the information to improve his guess, aka improve his prior, and the information is just the data samples coming in for the next message. The loss function is the total number of bits required for all the messages. Okay, so this is basically the compression that he's talking about here, right? Where your loss function directly optimizes data compression. The loss function is the total number of bits required for all the messages. In an autoregressive language model, for example, the messages are the word pieces the text is divided into. Okay, the word pieces the text is divided into is the tokens, so that's what we call that nowadays, but tokens are effectively just little chunks of words. The distribution encoding Bob's prediction for the first method is of necessity uninformed. So before you get your first message, your first piece of data, you're going to have to decide on some prior, and that first prior is going to be quite important. So what is it going to be here? They're saying a 0-gram prior based on the relative frequencies of different word pieces. This isn't super general, though, because here you're introducing the notion of relative frequencies of different word pieces. So I don't know. The transmission cost is the negative log probability under this prior. I don't know what they mean by transmission cost here. Bob then uses the first word piece to predict the second. On average, the second prediction will be slightly more informed than the first, and the expected transmission cost will be slightly lower. The process repeats with the predictions improving at each step. The sum of transmission costs is the negative log probability of the complete text sequence, which is the loss function minimized by maximum likelihood training. Okay, so kind of what they're talking about here, right? Autoregressive language model is trying to regress the next token based on the previous tokens. And here they're kind of showing that as you have more and more of the sentence, the probability of knowing exactly what that next token is higher and higher, right? You get more and more certain about what that next token is going to be. It is also the minimum number of bits that would be required for Alice to transmit the pieces to Bob using arithmetic coding. Yeah, so this kind of minimum number of bits idea here, this comes from information theory, which is, if you read that original information theory paper, it's like, it talks about this kind of idea of like, what is the minimum number of information that I need to send you in order to transfer some knowledge to you, right? And that's what they mean by bits here. But I always found it to be a little bit contrived. You know, this idea of like, I can send you 4 things and in that way tell you about more things. I don't know, maybe I'm just going to get distracted if I go in there. Bob and Alice are in nearly every paper about Bayesian statistics. IDK if they were in Bayes' original paper or something. Okay, so it is a reference to Bayesian statistics, I guess. There is a direct correspondence between fitting an autoregressive model with maximum likelihood and training it for data compression. Okay, so maximum likelihood is data compression. Okay. Autoprogressive networks are currently state-of-the-art for language modeling and in general perform well on discrete data where a natural ordering exists. You know, natural ordering here, is that a good assumption to start with? They had proved less effective in domains such as image generation where the data is continuous and no natural order exists among variables. There's no reason to generate one pixel before another. I don't know if this is necessarily true either. I think most vision transformers are assuming a specific ordering, right? You're kind of going through the image top to down, left to right. So there is an order that you're introducing there, and you are feeding it into a sequence model, and the VITs work pretty well, so I don't know about that. They also have the drawback of generating samples that require as many network updates as there are variables in the data. This is kind of interesting. So, require as many network updates as there are variables in this data. Generating samples. What does it mean by network updates to generate samples? Generating samples is inference, and you don't need any update to perform inference. Network updates, I guess, refers to steps in a gradient descent training process. This is the problem with these Bayesian papers, is that the terminology is very precise, and if you're not super aware of the terminology, you can kind of get lost in it. Diffusion models as an alternative framework that has proved particularly effective for image generation. In this case, the transmission procedure is a little bit more complex. Each message Bob receives is a noisy version of the message before, where the noise is designed such that its expectation the messages approach the data. Okay, noisy version of the message before. Kind of what it's referring to is you're adding noise to the message. So they really are setting up this, we're going to add noise and then give the message and then probably ask him to remove the noise. The transmission cost at each step is the Kullback-Leibler divergence. This is the KL divergence. The KL divergence is a distance metric between two distributions. So here you're going to be using the KL divergence between the distribution which Alice draws the message, which is the true prior, which is like the true distribution, right? Because Alice is kind of the oracle. She actually knows what the data distribution is, and Bob does not know what the data distribution is, right? So he's making predictions. And he's updating his distribution and here reparameterizing his distribution, right? His distribution, if it's a Gaussian, has some mean and it has some variance, and he's changing the value of that mean and that variance over time, hopefully trying to get as close as possible to the true distribution, which is what Alice has and what Alice is sampling from. The KL divergence will give you how much distance there is between Alice's distribution and Bob's distribution. So if Alice's distribution and Bob's distribution are the same, the KL is 0. So you're trying to minimize the KL divergence. The sum of the KL divergences is the evidence lower bound. So this is, now we're getting into a kind of this idea of variational inference, which is another kind of term here in Bayesian statistics, where basically the problem is you can't actually, if we actually look at Bayes' rule, so all of Bayesian statistics is based on this thing here, Bayes' theorem. Here we go. This was created by some guy called Bayes, and that's why it's called Bayes' theorem, and that's why Bayesian statistics is called Bayes' theorem. So you have two things here. You have A and B. And I guess, is this Alice and Bob? Yeah, actually, this might literally be why it's Alice and Bob. Okay, but you are, these are probabilities, right? And the P of A is basically the probability of A. P of B, vertical bar like this, A means P of B given A, and then P of A given B. So the P of A given B is equal to the P of B given A times the P of A over the P of B. P of A given B is the conditional probability. It's also called the posterior. So this is Bob's distribution. P of B is the conditional probabilities, can also be interpreted as the likelihood. So this is the likelihood here. What's the maximum likelihood is when you're trying to find. And then P of A, prior, and the marginal. So this is your prior, P of A, your assumption. So I was having a conversation with ChatGPT earlier today in preparation for this stream. And it gave me a really nice summary of this, which I think is a pretty good idea. So explain variational inference. In Bayesian statistics, we're often interested in finding the posterior distribution of some latent variables given observed data. So the posterior distribution is what Bob thinks, Bob's prediction of that distribution, right? So Bob's prediction of that distribution given some observed data, which is being given to you by Alice. Or Alice is the real world, right? She actually knows what the true distribution is, but all you can do is ask Alice to give you samples. Alice can't tell you what the true distribution is. So you have some prior, which is Bob's initial guess, right? 0 gram prior based on the relative frequencies. That's where that word prior keeps coming up. Parameters theta are the actual parameters of the distribution that Bob has. The likelihood px of the observed data, we want the posterior. What is the probability of this model being correct given that data? Here you have Bayes' theorem. The denominator p of x is also called the marginal likelihood or evidence, and it's often the challenging part. Okay, so that's where all of this comes in, right? It's hard to find this p of x. The integral is intractable. Can't find p of x. Okay, so what are you going to do if you can't find p of x? Well, here's where variational inference comes in. Variational inference provides a solution by turning the problem of computing the posterior distribution into an optimization problem. Okay, so we can't calculate this posterior distribution directly, but maybe we can optimize and over a series of steps get to a very good guess of that. So instead of computing the true posterior, VI, I don't know what they mean by VI here. Variational inference proposes a family of simpler tractable distributions, Q. Okay, so let's make a guess, Q. The closeness between two distributions is KL. Okay, so we are guessing that our posterior, we're going to replace it with a guess called Q, and then we're going to measure the KL divergence between Q, which is our guess, and then the true posterior, P, which we can't calculate directly. Natural order is the underlying structure we keep getting hints at. R equals 1 for Q Laura, etc. I think natural order is more the central limit theorem. So there's a video on this that I would recommend. Central limit theorem, 3 blue, 1 brown. Yeah, this guy's YouTube channel is really fucking good, BTW. But basically, this guy, in this paper, he basically explains why the Gaussian is such a good guess, and there's kind of fancy math reasons for it, but he's kind of showing you here why it's like symmetry in the symmetry of the Gaussian is the reason why it ends up being important. But basically, TLDR, the Gaussian is a bizarrely universal good prior. So almost always assuming that your prior is Gaussian is a good guess, right? So I think whenever here they're talking about discrete data where natural ordering exists, kind of what they're hinting at is that this discrete data is natural, and natural in the sense that if you were to assume a Gaussian prior, it ends up being a pretty good prior. But that's just because we've observed that in a bunch of other natural systems, a Gaussian prior is a good prior. Okay, but we were talking about how the evidence lower bound kind of comes out of this KL divergence. Okay, so we want to minimize this KL divergence, right? We want to minimize our guess at the distribution, this Q, with the actual distribution, this P. So we can't directly minimize KL divergence. We can maximize instead what is called the evidence lower bound, which is a related. So the evidence lower bound is this. It's the log of this minus the log of that and the expected value of that. And that's going to be a lower bound on this KL divergence. And that you can actually calculate. You can actually optimize with respect to that. So now that you can actually optimize with respect to the parameters lambda of your guess here, that means that you can use gradient-based optimization methods to eventually approximate this Q, and that Q is going to be close to the true posterior, which is this one here, which is what you really wanted. You really wanted this here, P of theta given X, which is basically how good is your model at modeling this X. So that's what KL divergence, that's what evidence lower bound is. And I would definitely recommend 3 Blue 1 Brown's videos on those types of statistical concepts and why they make sense. Okay. It is also expected number of bits needed to transmit the data using an efficient bits-back coding scheme. Okay. Once again, there is an exact equivalence between the loss function used to train the model and the model's ability to compress data, as elucidated by previous authors. Is this also his paper? What is this paper? Practical lossless compression with latent variables using bits-back encoding. 2019. Okay, I do not know about that, but we'll see. We posit that the superiority of diffusion over autoregression for image generation lies in the way diffusion progresses from coarse to fine image details as the level of noise decreases. Is that true? I don't know if this is necessarily true. I know that usually there's noise schedules, right? So usually for image diffusion models, the amount of noise and the kind of nature of that noise changes depending on where you are in the diffusion process. But coarse to fine image details, I mean, are we talking about semantic coarse to fine details? Are we talking about like the shape of a cat versus the texture of a cat? Or I don't know, I guess it depends on what your definition of coarse to fine is there. A more natural way, when you're using the word natural in a math paper, it just kind of is a little weird. To construct an image one dot at a time. However, diffusion has yet to match autoregression for discrete data, which is unfortunate, as diffusion models have the advantage of decoupling a number of generation steps from the number of variables. A fundamental challenge is that when the data is discrete, the noise in the diffusion process is also discrete and therefore discontinuous. When the data is discrete, the noise in the diffusion process is also discrete. Because you need to, if your data is discrete, right, as in it's one of X tokens, then the noise that you're going to have to add to that token, to that set of tokens, you're going to maybe say, okay, rather than this token, it's going to be this token instead. So if you have a coin flip and you're measuring coin flips, right, you can't add not like the noise that you can add to that is change. Okay, rather than heads, we're going to pretend that it was tails, but that noise is discrete. So maybe that's, and therefore discontinuous. And as soon as you have something that discontinuous, it's not differentiable, which then means you can't push gradients. The return to the transmission metaphor, if the data is a piece of text, then Bob begins the process with a totally garbled text, every symbol of which is either randomly altered or left unchanged by each of Alice's messages. So there's kind of a diffusion on text, I guess is what's happening here, which is kind of cool to think about, right? Imagine if you had like a sentence of just garbled tokens, and then as you got more information of the true distribution, right? The distribution that Alice knows, Alice's nature, and she knows the true distribution, and she's giving you little messages that hint at you and give you an idea and let you better and increasingly better and better predict and model the distribution that only she knows, but you, Bob, don't know that. And your piece of text, your sentence, is really just a choice of discrete tokens at every single position in that sequence. So you have to switch each token eventually to the right one. John Ryan here with some knowledge bombs. Let's see. I think what we mean by natural order is that sometimes the variables you would want to sample don't have an order if you are looking at a sampling or a 1D sequence. Oh, okay. So you're just literally saying it has a order as in it's a sequence. If you are attempting to sample from a picture with pixels, there is no particular natural order. By making it a sequence, we are imposing an ordering which might be absolutely work but not necessarily the best way. Okay. So ordering is maybe key, is what you're saying. A key motivation was our belief that the fully continuous transmission process where Alice's messages smoothly alter Bob's belief. So somehow you have continuous messages coming in rather than discretized messages, but it's kind of weird. I don't know if you're going to be able to do that with a classical computer. Would be more effective for discrete data. This should open the door to gradient-based guidance and few-step generation, similar to those that have been developed for continuous diffusion. Okay. Bayesian flow networks, the model introduced in this paper, differ from diffusion models in that the network operates on the parameters of a data distribution rather than on a noisy version of the data itself. So what you're removing the noise from are the parameters of some data distribution. So you're removing the noise from a mean and a variance of a Gaussian as opposed to the image itself, right? So in a diffusion model that you would use, such as stable diffusion, you're adding noise to the actual image, which is supposedly a sample from your distribution of all images. But here you're going to be performing diffusion on the actual parameters of the data distribution of which you are starting from this prior, which is basically a Gaussian. This ensures that the generative process is fully continuous and differentiable, even when the data is discrete. BFNs can be summarized by the following transmission scheme. Bob has an input distribution, which is initially a simple prior, okay, a standard normal, and a uniform categorical for discrete data. So a uniform categorical distribution is just a distribution that is equal mass for every single category. So a uniform categorical distribution example would be CFAR 10, right? Because CFAR 10, it has 10 possible categories, right? And every single category has exactly 6,000 images per class. So it's perfectly uniform, right? If you had many more pictures of birds than you had of cats, then it wouldn't be uniform, but here it is, because there's exactly this amount of images per class. It's balanced, perfectly balanced, as all things should be. At each transmission step, he feeds the parameters of the input distribution, in this case the mean of the normal distribution and the probabilities of a categorical distribution. So probabilities of a categorical distribution, that's starting to look a lot like the next token prediction, right? You're saying out of all these next tokens, which one has the higher probability of being the actual token that I want into a neural network. The network outputs the parameters of a second distribution referred to as the output distribution. Okay, so you start with a guess of the input distribution, and then you output an output distribution. And you can see how slowly over time, right, you're kind of performing this variational inference where you're kind of getting a better and better version of this Q, which is a guess to your P, which is what you really want. So over time, your output will begin to match the true distribution. Alice then creates a sender distribution by adding noise to the data. according to a predefined schedule. Okay, so we have noise schedules as well here. And Bob creates a receiver distribution by convolving the output distribution with the same noisy distribution used by Alice. So this idea of like convolving actually is perfectly coming from, makes a lot of sense given this central limit theorem video from 3 Blue 1 Brown. But basically one of the things that he shows is that you can basically, if you convolve two things over and over again, you kind of end up with the Gaussian. So convolution ends up looking like a Gaussian. Intuitively, for every value that data could take on, Bob constructs the center distribution would have used if the value was correct, then sums up over all these hypothetical center distributions weighted by the probability of the corresponding value under the output distribution. Alice picks a sample from the sender and sends it to Bob at a cost equal to the KL divergence from the receiver to the sender. Bob then uses the sample to update his input distribution following the rules of Bayesian inference, and then the Bayesian updates are available in a closed form as long as the input distribution models all of the variables in the data independently. How strong is this how strong is this assumption? Once the update is complete, Bob again feeds the parameters of the input distribution to the network, which returns the parameters of the output distribution. The process repeats for n steps, at which point Bob can predict the data accurately enough that Alice can send it to him without any noise. Okay, so you still have some n-step process here, so I don't know why they were spending all this time talking about continuous when you're still discretizing it here in some number of steps. All right, let's look at this figure 1. So we have some network. The network is receiving as input these distributions, the mean of a normal distribution and the probabilities of a categorical distribution. Right, so here you have the probability. This is a 3 possible outputs. This is a ternary symbol sequence. So ternary just means 3, and ternary symbol sequence means that basically there's one of 3 variables. It's a sequence of variables. It's a sequence of letters, of symbols, and those letters are going to be A, B, or C. So there's some probability that the next one is A, the next one is B, and the next one is C. And the first 2 variables, B and A, are shown. Okay. Each step, the network emits the parameters. Emits, kind of a weird choice of word there. You mean outputs the parameters of an output distribution based on the parameters of the previous input distribution. So here's the output. It's a probability for each of the 3 discrete possible tokens in this sequence. All right, so this is, it has to be A, B, or C, so it seems here that A is the most likely one. That's variable 1. Here we have variable 2. Now it's a slightly different distribution. The sender and receiver, which are both continuous, are created by adding random noise to the data and the output distribution respectively. So this is the actual data, right? So Alice is nature. She knows the actual true distribution, and in this case, the true distribution, you're going to pretend that your data is your true distribution, right? If you have a big enough data set, your data set distribution basically models the actual distribution. So we see here how Alice's data set says that the next token is B. I know that the next token here is B, versus here she says, I know the next token is A. And then all that our network output is, here's what I think the probabilities for the next token are. Alice is going to add some noise to this data and then give it to this, and then we're going to get, I guess, the receiver distribution and then the sender distribution. So the same noise gets added to both of them, and then you're saying, okay, well, if I add this noise to the my current guess here, this is the distribution that I end up with, and I'm going to call that the receiver distribution. And Alice knows what the actual data set is, so she knows what the true data distribution is, or at least some guess of it. She adds the same noise that you're adding to Bob's guess, and she gets her own distribution here. And this KL here is the KL divergence between these two. And interestingly, the reason that this is a arrow like this, and it doesn't have 2 things, is that the KL divergence is not symmetrical. The KL divergence between A and B is different than the KL divergence between B and A, which is kind of weird to think about, but it still works. So once you have the KL divergence between those, sample. The KL divergence is the loss, so at some point the loss is coming in this way. I don't know where the loss is, but the loss is the KL, so it has to be somewhere around here. Then I guess you sample from the center distribution, and then you use that to update your guess, and then your guess is then fed into the network again. And then you have this kind of iterative process of improving your guesses. And you can see how over time, basically, this guess here, which is here it's output, but it's basically the input from the previous, or it's the input from the previous step, output from the previous step. Over time, this is going to get better and better at matching this. And if this is better at matching this, then when you add noise to both of them and that noise is the same, then these distributions are going to be the same, which means your KL divergence is going to be very small. So over time, your KL divergence will get smaller and smaller and smaller and smaller, which means that the distribution that Alice knows and that Bob is guessing at will get closer. And if you know what this distribution here is, then you can basically just guess what the next token is. Let's see. A sample from the sender is then used to update the parameters of the input distribution following the rules of Bayesian inference. Conceptually, this message sent by Alice to Bob and its contribution to the loss function is the KL divergence from the receiver to the sender. Okay. How many of you guys are still here? Note the key difference between the input and output distributions. The input distribution receives information about each variable in the data independently via the Bayesian updates, and is therefore unable to exploit contextual information, such as neighboring pixels in an image or related words in a text. The output distribution is produced by a neural network that jointly processes all the parameters in the input distribution, giving it access to all available context. So here they're talking about the input distribution versus the output. So the output, you're just kind of getting this magic set of probabilities for each possible set of tokens. But here you're also have access to the other probabilities. Is that what they're kind of saying? The combination of the input and output distributions represents a division of labor between Bayesian inference and deep learning that plays to both of their strengths. The former provides a mathematically optimal and finely controllable way to collect and summarize information about individual variables. So it's Bayesian inference. It gives you a mathematically optimal and finely controllable way to collect and summarize information about individual variables. And then deep learning integrates information over many interrelated variables. Where is the actual network loss coming in from? I think it's literally just here. So the deep learning part is just here. You have your loss, and it's going through this receiver into this output here and then into the network, and that's how you're updating the parameters of this network. And that's your deep learning part. And your deep learning part sees all of the variables at the same time. So it has kind of a context that includes all the variables, so it can potentially make, it can look at the interdependence between those variables, versus this Bayesian update is only for this specific variable here. What do they mean by variables? Is that just the variables of the parameters of the data distribution? How are we picking these? The above transmission process defines an n-step loss function that can be generalized to continuous time by sending n to infinity. Okay, so there we go. So the way that they're going to make this continuous is by saying n is infinite. The continuous time, the Bayesian updates become a Bayesian flow of information from the data to the network, as well as removing. So in the limit to infinity, Bayesian updates become a Bayesian flow. And that's, I guess, where the name Bayesian flow network comes from. As well as removing the need to predefine the number of steps during training, the continuous time loss function is mathematically simpler and easier to compute than the discrete time loss. Huh. A BFN trained with continuous time loss can be run for any number of discrete steps during inference and sampling, with performance improving as the number of steps increases. What is going on here? He keeps just like flip-flopping between continuous and discrete. Continuous time loss can be run for any number of discrete steps, but you're still doing it. I think maybe there's a distinction here between discrete steps and discrete time. The rest of this paper is structured as follows: a short summary of related work, the basic framework of BFNs, along with the general derivation of the continuous time loss functions, specializations of the framework to continuous, discretized, and discrete data are provided in sections 4 and 6, pseudocode, and experimental results on CFAR10 and binarized MNIST. Okay. So, I mean, so far kind of what I've gotten here is that you're using this Bayesian update. You have continuous time Bayesian updates become Bayesian flow, but you're still discretizing it and doing it in steps. You also have a deep learning component or a neural network here that is trying to match this sender distribution, which is a noisy version of the data, with this receiver distribution, which is a noisy version of your previous best guess. And your network, which parameterizes this distribution here, right? It's just giving you a bunch of means and variances that define that, right? Is trying to basically predict that. So your network is predicting a bunch of Gaussians. Okay. Most closely related to diffusion models. However, they differ in some crucial aspects. BFNs embody a function from one distribution to another, rather than from data to distribution. I mean, rather than from data to distribution, I mean, the distribution is coming from the data, so I don't know what the fuck they're talking about there. The this sender distribution is effectively the data distribution, so like diffusion models and most other probabilistic networks, one advantage is that because the parameters of a categorical distribution are real valued probabilities, right? So the parameters of a categorical distribution are real valued probabilities. What do they mean by that? Is that this categorical distribution, right? There's only 3 categories, A, B, or C. The parameters of this, if you were to describe someone this distribution, what would you need to describe someone this distribution? Well, you would need to tell me what the probability of A is, what the probability of B is, and what the probability of C is, right? If I wanted to describe someone a Gaussian, I would need to tell you the mean, and I would need to tell you the variance. So the parameters of a Gaussian are different from the parameters of this discrete categorical distribution. But the parameters of this discrete categorical distribution are just simply however many categories you have. You just need a probability for each of those, right? So the parameters of a categorical distribution are real valued probabilities. The inputs to the network are continuous even when the data is discrete. Okay, so the data itself is discrete in that it's only going to be A, B, or C, right? It's a categorical distribution, but each individual point of data that you sample is only going to either be A, or it's going to be B, or it's going to be C. So that's different from what the network is getting. This neural network is receiving the parameters of the distribution, which is probabilities for this categorical distribution. This contrasts with discrete diffusion, which natively uses discrete samples as input. Okay. Numerous authors have proposed continuous variants of discrete diffusion. Typically, these rely either on mapping to and from a continuous embedding space, or on restricting continuous diffusion to the probability simplex. I'm just going to take that as is. While we do not directly compare against the above methods, we note that continuity is an inherent property of the Bayesian flow framework. Networks input automatically lie on the probability simplex by virtue of being the parameters of a categorical distribution. So what do they mean by lie on a probability simplex here? What they're saying is that the network inputs, which are these parameters of this categorical distribution, which are just the probabilities of each individual thing, are on this simplex, which is, for 3 variables, it's a triangle. And that's actually where, so we're going to do a little skipping here, but in the figures of this paper, let's minimize a little bit so we can get here, not here, which is the figure that I used for this thumbnail. Let's go, let's keep going, let's keep going, let's keep going. Holy shit. That's not it either. This is what I want. So this is the probability simplex for the A, B, and C distribution, right? So simplex for a coin, right? A coin can only be heads or tails, so it's a line. It's heads on one side, tail on one side, and somewhere in between is a point that says what the probability of heads versus tail is. If you have 3 things, if you have in the example that they give where there's A, B, and C, A, B, and C are the 3 parts of this triangle. So you have A in one corner, B in one corner, and then C in one corner. So the probability, if you were here in this corner, then it's 100% A. If you're in between A and B, then it's 50% A, 50% B, right? So you can actually, let's duplicate this just because I want to have this figure open when I show you guys, but let's say here, right? So A, B, and C here, we see how it's mostly A, a little bit of B, and a little bit of C. So if we had A, B, and C, the point would be a little bit of A, or mostly A, a little bit of B, and then very little C. So it'd be kind of a point here, right? So this, these probabilities for each of these things would be a point on this simplex, right? And I think here they're basically, there's well, actually, let's not get to there, but I basically just mostly wanted to explain what this point here is, where the network inputs automatically lie on the probability simplex by virtue of being the parameters of a categorical distribution, rather than constraints added to an existing system, as well as reducing the number of free parameters and design choices, the continuous embedding space, the mapping functions. Okay, so if you have, here they're mentioning that other people have tried continuous variants of discrete diffusion, and part of that involves mapping into some continuous embedding space. Any kind of mapping function, you're going to have to store that, right? So reducing the number of free parameters. So if you don't have to waste parameters to keep track of this mapping function, then that's less shit that you have to do, which is, you're not trying to do more shit. So here they're saying that BFN is better than these previous approaches because you don't have to have this mapping function. This ensures that BFNs directly optimize the negative log likelihood of discrete data, unlike continuous diffusion methods for discrete data, which typically require either simplified loss functions, auxiliary loss terms to make the learning stable. Okay. For continuous data, BFNs are most closely related to variational diffusion models. Diffusion models that are doing variational inference with a very similar continuous time loss function. The main difference in this case is that the network inputs are considerably less noisy in BFNs than in variational diffusion. Are they noisy? I don't know, it kind of seems pretty noisy based on here, right? If this is the path, right, up here in the image, right, our distribution guess, the guess of the distribution that we're kind of iteratively refining over time is just 3 probability values for each of these categories, right? So if this is 1 point on the probability simplex, right, this here, which is a distribution, is a point on this probability simplex for 3 possible categories. If that is 1 point, then at this iteration, this is a slightly different point. So over time, we're kind of taking a path, right? What we're really doing is we're moving around in this probability simplex and getting to a certain point. So this is the path that we're taking over the course of our optimization process through this probability simplex. So I don't know, kind of what I was getting at is that I feel like this is a little noisy. So I don't know what they're saying here, that it doesn't have noise. Considerably less noisy in BFNs. Does that look considerably less noisy to you? Because the generative process of BFNs begins with the parameters of a fixed prior, whereas that of diffusion models begins with pure noise. So in a BFN, you're starting with a prior, and then you're learning the parameters of that prior distribution, versus in diffusion models you start with pure noise because you're starting from the data itself. We hypothesized that the reduction in noise could lead to faster learning on large data sets where the model underfits. So underfitting is where your model has more juice to give, right? Overfitting is when the model has kind of memorized the data and overfit to it. Underfitting is when you could train longer and it would be better. It's kind of a Eli 5 overfitting, underfitting. However, we have yet to test this hypothesis experimentally. Okay. It's kind of a weird thing to mention there. Another key difference from diffusion models is that there is no need to define and invert a forward process for BFNs, which arguably makes it easier to adapt them to different distributions and data types. We showcase this flexibility by adapting BFNs to continuous, discretized, and discrete data with minimal changes to the training procedure. This contrasts with discretized diffusion, which requires carefully defined transition matrices. Okay, I'm not like super fully understanding everything here, but it seems like basically BFNs are a type of continuous diffusion model where rather than trying to denoise the data itself, you're denoising your guess or your prior of the actual distribution. This section covers the basic mathematical formalism of Bayesian flow networks. All right, we're getting into the math here, laying out the structure of the various functions and distributions required by the model, along with the discrete and continuous time loss functions used for training. So 2 different loss functions depending on whether you're discrete or continuous time. Given d-dimensional data, x1 all the way to xd in some d-dimensional data space, let theta 1 all the way to theta d be the parameters of a factorized input distribution pi. Given theta. So if this is a Gaussian, then this would be the mean and the variance. the pi of x given theta, which is this part here. We go to Bayes' theorem, px given theta, right? Which is known as the likelihood of the observed data x. How likely is this data x if we know if we have some model theta, right? So that's the difference between these two terms here, right? So p theta given x is what is the probability, even though it's not really the probability, but what is the probability of our model theta, the parameters of our model given some input distribution x, versus p x given theta is what is the probability or the likelihood of our data x given our model theta. So here we're talking about probability of this data given this model theta. Well, in order to do that, you just multiply all these probabilities out, right? The probability of one thing and another thing and another thing and another thing, you just multiply those out. So 50-50 chance twice is 50% times 50%, 25%. So multiplication is how you add up probabilities. So here you're multiplying over all of the dimensions, and you're saying each individual x for the theta that parameterizes that particular dimension of x. Theta d may consist of the probabilities of a categorical distribution. So if you have a categorical distribution such as the number of, or such as a discrete set of tokens, then your probabilities for each one is going to be the parameters of that distribution. Let PS of something given x and a be a similarly factorized sender distribution. Okay, so the sender, we need let's go back up here. I think it's useful to have these figures up when we're looking at these. Here we go. This is trash. So the input distribution is this one, right? It's your guess. It's Bob's distribution. And then the sender distribution is this one here. It's Alice's distribution. So Alice's distribution basically has all the same things, except it also has this alpha, right? And the probability of y, which is some other d-dimensional data, maybe it's the answer, you know, the data itself, this thing here, this is y. Very similar thing. Actually, this is not a similar thing. This is probability of y given x. So here you were saying, what's the probability of this data given we have some prior or input distribution parameterized by theta? Now you're saying, what is the probability of y given the x? But then also this alpha. So what is this alpha? This alpha, which is a number, is an accuracy parameter defined such that when alpha equals 0, the sender samples are entirely uninformative about x, and as alpha increases, the samples become progressively more informative. Okay, so alpha is some notion of how useful the samples are that are being sent here. So there's some kind of importance weighting or something like that, you know, something that over the course of this training, you're saying this data is more garbage or this data is more better. And that is being passed in through this alpha, which might actually be the schedule that they're talking about. They mentioned that they're using a schedule somewhere up here. But that might be what the alpha comes in as. Output distribution. During the data transmission process, the input parameters theta are passed along with the process time t. Okay, so very similar to diffusion models, where the diffusion model gets the time t because the time t is indicative of how far along this diffusion process you are, right? Which lets you know that at the beginning of the diffusion process, you can probably make big changes to these input parameters. You can probably remove big chunks of noise. But once you get closer to the actual final time t, you want to be making increasingly smaller and smaller changes to these thetas. As inputs to a neural network psi. Okay, so you have some neural network psi. Your neural network psi takes in your thetas, which are the parameters of your distribution, aka your means and or variances, or your probabilities for each of the different categories. And this network outputs a vector, psi1 theta t, psi d theta t. Okay, a vector for each dimension of your data. So your data has some dimensionality. Here, the dimensionality of the data is 3, right? So in all the examples, I think the dimensionality is always 3, just to make it easy to plot and easy to show in figures. But of course, you could have much higher dimensional data. In CFAR 10, the dimensionality would be 10 classes, 10 categories. Your distribution has 10 possible categories, which is used to parameterize an output distribution factorized in the same way as the input and sender distributions. Okay, so basically the only thing we've done here is we went here. You see how this input distribution is x given theta. Now you have the same thing. You have x given theta comma t, and we're replacing this here, this theta here, rather than saying what's the probability of x given our model, which we can't do, right? As we saw here, this part here is hard. It's hard to find the value of this. But we have a guess, and we're going to be using our neural network to give us that theta. And this neural network basically gives you better and better and better thetas. So the first theta is going to be shit, and then the next theta will be a little bit better, and the next theta will be a little bit better, and the next theta will be a little bit better. And that seems to be this kind of process of this network basically over time gives you better and better thetas, and the thetas are just the probabilities of each of these 3 tokens. The key difference between the input and output distributions is that while each P input depends only on the information gathered via P sample, what do they call it? Sender, P sender, sorry. So PS is sender, PI is P input. About XD, each P output depends on all of the theta, and hence all of X. Interesting, okay. So what they're saying here is that the Bayesian update, based on this noise and the sender distribution, the receiver distribution here, is specific to one variable, which is only one dimension of the distribution, right? So you're only aware of the single variable here, versus the neural network is aware of all the variables, right? So there's a dot here. You see this dot, dot, dot. That dot, dot, dot is because there's d dimensions. So you're kind of alternating between something that is aware of everything and can model possible relationships between those things, which is this network, the neural network, which you're updating with gradient descent. And then you have this Bayesian update, which is specific to only a single variable, right? Which is what they're saying here. PI depends only on the information gathered from the P sender about a specific XD, versus the output depends on all of the thetas, and then all, which means all of the dimensions of X. The output distribution, unlike the input distribution, can therefore exploit context information such as surrounding pixels in an image or related words in a text. And the way that this is written is not just surrounding pixels in an image, it's the entire image, right? Like I think one thing that I'm kind of immediately noticing here is that this is very beautiful, this Bayesian flow network, in the sense that it's very clean and simple, but it's also kind of cursed, in some sense. This is going to work great when your capital D here, your dimensionality is 3 or 2 or 10 or something simple like that. But what if it's a 1024 by 1024 image? now this is monstrous. Like, you're not going to be able to do that. You're not going to be able to feed these huge, highly dimensional things into a neural network. At some point, you're going to run out of GPU memory. So that's kind of usually ends up being the case, that with a lot of these variants or kind of new ways of doing machine learning that are much more based in terms of the math and the theory behind them, part of the reason that a lot of times they don't end up working out is because just the way that they scale and the way that you can implement them on a GPU is trash, right? So there was capsule networks is the kind of famous example that I love to bring up, but capsule networks was supposedly going to be the end all be all, right? It was basically we were going to run away from convnets and we were going to basically do these capsule networks, and they're so much better and it's totally what the brain does and it makes a lot of sense, but they're just not very good. They're much worse at scaling than your CNNs or your VITs or anything like that, so then just nobody uses these anymore. So it could be the case that there's a similar thing here where in this paper, like, it's beautiful and he's going to show you a bunch of math on how it all works out, but all the examples are MNIST, CFAR, and then these toy examples with only 3 dimensions. So I don't know. I'm not going to hold my breath until someone shows me that these Bayesian flow networks can work for a vocabulary or a tokens with 30,000 possible tokens. Okay, rant over. Let's see. Receiver distribution. P receiver, you have theta, you have T, and you have this alpha, which I think is the schedule, but they haven't exactly mentioned that. Given the center distribution and the output distribution, PO, PS, the receiver distribution over YD is defined as this. So the receiver distribution, which is what is Y, which is this. Let me go here. The receiver distribution, one of these is Y. What is Y? Given theta, the models of our, or the parameters of our statistical model, of our categorical distribution, T, which is how far along this optimization process we are, and then alpha, which is kind of the schedule, is equal to the expected value of the output distribution, or the expected value of the center distribution given this output distribution. Intuitively, this can be understood as a receiver who knows the form of the center distribution, but does not know x, and therefore integrates over all x prime and hence all possible center distributions weighted by the probability given to x prime by the output distribution. The receiver distribution therefore combines 2 sources of uncertainty, the known unknown of the center distribution entropy and the unknown unknown of the output distribution entropy. Okay, let's try to make sense of that. The receiver, this person here, who knows the form of the center distribution but does not know x. So the receiver knows this distribution here but doesn't know this, right? The receiver doesn't actually have access to the actual x or the data itself. The receiver only knows this center distribution, which is the x plus the noise, and therefore integrates over all x prime and hence all possible centers. This doesn't make it. Weighted by the probability by the output distribution. Okay, so I guess here what they're saying is that the receiver knows this output which is coming from the network, so the network has access to all of the x dimensions. So this here is kind of a guess based on all the x dimensions, which is I think what they're talking about here. And M with these data. And with these data. I don't know what you mean, War. I'm sorry. Weighted by the probability given to x prime by the output distribution. The receiver distribution therefore combines the uncertainty, the known unknown of the sender distribution entropy. Matthew Roman, thanks for the 5. I'm always confused why people watch these streams, you know. I'm just some dude trying to figure things out. You know, I wish I was as cool as Alex Graves and I could just like theorize these things, but I'm just a normie, you know. I have to figure these things out manually, which is a function of alpha and the unknown unknown. So the sender distribution here has this dependency on alpha. So therefore the entropy of this sender distribution is also going to be a function of alpha. And then the unknown unknown of the output distribution entropy. So the output distribution has some entropy, but this receiver is not aware of that. True genius is the ability to get over your head. Yeah, I think that's kind of what I'm hoping for with this channel, you know, is kind of show people what it actually looks like to read research papers and kind of do machine learning. You know, it's a lot of just staring at shit and then slowly figuring it out and still not really figuring it out. Bayesian updates. Okay, so Bayesian updates is this step here, and this is how you're going to use your previous input and update it with what you just learned from this noisy comparison between the sender and the receiver. So given the parameters of the sender, of the distribution, your current guess, and sender sample y drawn with accuracy alpha. Okay, so the sample y is drawn here. So this is the y. So you're drawing this from your data set, right? You have your data set of 10 million images, and then you're sampling one piece of that, one image, and that's your data here. And the Bayesian update function h is derived by applying the rules of Bayesian inference to compute the updated parameters theta prime. Okay, so now here's where you use your Bayesian statistics to update the parameters theta prime, and this Bayesian update is specific to a single variable, so you're only going to be updating one variable here. Theta prime, which is going to be your new parameters of this distribution. The Bayesian update distribution is then defined by marginalizing out y. So you're pulling out y here. The multivariate Dirac delta distribution centered on the vector A. What? What just happened here? 4.4, we provide both forms considered in this paper have the following properties. The accuracies are additive in the sense that alpha equals alpha A plus alpha B. All right, let's try to figure out what the fuck is going on here. So we're introducing a new Bayesian update distribution, which I think is what's going on here. So when you're doing this variational inference, right, and you're crafting this evidence lower bound, you're saying that, hey, I don't know what this p theta given x is, but I can come up with some new distribution q here, though. And that new distribution q, I'm going to basically improve over time, and I guess that's maybe what this is. This PU here, this Bayesian update distribution. The Bayesian update distribution gives you theta prime given theta. Okay. And it also given x and alpha. That's the expected value of the difference between theta prime, which is your updated variables, and h theta minus theta h, which is a function of theta y and alpha. Let's get more intuition on this term here. Multivariate Dirac delta distribution. So I know what the Dirac delta function is, but what is the Dirac delta distribution? It's a generalized function or distribution whose value is 0 everywhere except at 0 and whose integral over the entire real line is equal to 1. So a distribution, a probability distribution, has to have an integral equal to 1, right? Which is why, for example, here you have a normal distribution. Normal distribution looks like this, e to the negative x squared. If you see that, that's the Gaussian right there. But then why the fuck are they doing this 1 over b square root of pi? The reason you do that is to normalize it. So Gaussian distribution right here. Let's do one with the, yeah, here. So what is this shit here? The reason this shit is here, these terms before this e, is so that it becomes 1. So the area under the curve is 1. But the shape is basically just e to the negative x squared. That's where that shape comes from. Centered on the vector A. We'll prove that both forms, Pu, considered in this paper, have the following property. The accuracies are additive. Okay, so now they're saying Pu theta prime prime. So a different guess. Okay, so they're applying this thing twice. So you see here how they basically said, here's what Pu means, and then we're going to basically plug that in, and now we've, instead of Ps here, now we have Pu. And then we have different alphas for A and B. Given the prior input parameters theta 0, the probability of observing parameter theta n after drawing a sequence of n Sanders samples. So here you're changing your parameters theta over n steps, right? And every step you're going to get a new sample. So here you have one y, one step, y1. So this is y1. If we were to look at the next step, it would be y2. And you would have, here is theta 0, or theta 0, theta 1, y1. Next step you would have theta 2, y2. So here you can see that you're updating theta over time, over a bunch of steps. And we know from the abstract, or not the abstract, but the introduction, that we really just want n to go to infinity. And alpha is the accuracy at each sample. So I guess at the beginning you're going to have a different schedule, and you're going to say the y's that I'm getting now are not as good as the y's that I'm going to get later, which is kind of weird to think about. Like, how does that actually work out? Like, what is an actual alpha schedule for this? I don't know. Expected value. The expected value of the expected value. So you see how they're just chaining these expected values together. Theta 1, theta 0, theta 2 given theta 1, theta n minus 1 given theta n minus 2. So they're kind of stacking this all the way to infinity, all the way to theta n. And I bet you they're going to basically eventually put a limit to infinity, and then, okay, maybe not. But if you were to stack all of these expected values like they're doing here, this e, eventually you get to Pu, the Bayesian update distribution of theta n given theta naught and x, and the sum of all the alpha i's, which they're saying is basically this. So all the alpha i's sum up to alpha, and they told us that alpha is some number above 0. Okay, the puzzle is getting maybe a little bit less clear, but we're making a little bit more progress. Accuracy schedule. By performing an infinite number of transmission steps, the Bayesian update process can be generalized to continuous time. Let t go from 0 to 1 be process time, and let alpha t greater than 0. So you see this? Boom. We called it. We knew it. As soon as we saw that, I was like, I bet you this fucking alpha is going to be a schedule. And here we go. We have the proof. Alpha is a schedule. Alpha is going to be a function of t, and over time, you're going to change it. Okay. So alpha, which is going to be a function of t in between 0 and 1, is going to be the accuracy rate at time t, so you're going to have some accuracy schedule. The accuracy schedule, which is going to be beta t, is just a function of this alpha t. And you have an integral from time t equals 0 to t, and you're just integrating that alpha, which probably comes from this summation over all alphas. This almost like feels like the discount rate in reinforcement learning, right? Doesn't that kind of like rhyme with the discount rate a little bit? You have this thing that like slowly accumulates, and as it becomes bigger and bigger and bigger, you get more and more certain that the quality of those samples is better. Kind of has like a similar kind of vibe to me. Maybe this part is like stable diffusion. I remember that DDIM uses a changeable time schedule like alpha 1, alpha 2. Yeah, Yujun Liu. I think you're on the right idea right there. I think this alpha is also a schedule. It follows from the above definition that b of t is a monotonically increasing function, so it always gets bigger. As if you make t bigger, b is going to be bigger, which means that your derivative is always going to be, not your derivative, but you're always going to have a bigger b of t over time. B of 0 is 0, and that dB dt is alpha of t. Okay, so b of t is basically the rate of change of this accuracy schedule is the alpha. Specific forms of b of t for continuous and discrete data are provided. I'm curious. Accuracy schedule for continuous data is the input distribution linearly decreases with t. Information flows in the input distribution at a constant rate. But where's the schedule? So here's what alpha of t equals. B of t is this. Alpha of t is this. So now the question is, okay, we've redefined alpha of t into now be a function of these sigma, but what is that sigma? Sigma is the standard deviation of the input distribution at time t. Okay, all right. This makes more sense. So over time, the distribution, this input distribution, right? Assuming it's a Gaussian, assuming it's like this, right? It's a little Gaussian. It's going to have some sigma, which defines how spread it is, right? Here, the sigma, when it's very big, it's very spread. So you see how this yellow one, big sigma, big spread, little sigma, little spread, right? And the spread is basically how confident you are. So this distribution here, this blue one, if you were to sample from that, you would pretty much almost always get a number that's close to 0. Versus if you were to sample from this golden line here, which has a big sigma, you're going to get shit all over the place, right? So if you have these distributions and you're iteratively refining those distributions, it makes sense that the sigma is probably going to get smaller and smaller and smaller. So like you're going to get more and more certain about like what that exact, where and when that exact peak is in that Gaussian. So it kind of makes sense that there's a relationship between the standard deviation of the input distribution and the schedule that you're using, right? So as you get smaller and smaller spread, your Gaussian becomes more and more like, yup, it's right here, and it's going to be that thing, right? Then the schedule is going to change. Okay, that kind of makes sense. Both are derived using simple heuristics with a deeper investigation left for future work. Okay, that's a little leave it for future work. The Bayesian flow distribution. Given prior parameters theta naught, okay, so theta naught is basically your first guess at the prior, which is the distribution that you're starting with, which is going to be a Gaussian or a categorical distribution. Bayesian update distribution PU and accuracy schedule beta T. The Bayesian flow distribution PF is the marginal distribution over input parameters at time t. Okay, so they introduced this Bayesian update distribution PU, but now we have the Bayesian flow distribution PF. And PF, which says, okay, what is the probability of this model given my data x and time t, is equal to PU at some theta, or PU of that theta, given theta naught, x, and beta t, or beta, which is your schedule. So if Bayesian flow, see how here at the beginning they said Bayesian flow is the limit of Bayesian update as you go to infinity. Yeah. In continuous time, the Bayesian updates become a Bayesian flow. So Bayesian update is discretized, Bayesian flow infinite, right, as you go to infinity there. So that's kind of seemingly what's going on here, is they're saying here's the Bayesian update, which is step by step. You see these Bayesian updates, you're doing little steps, little steps, little steps, little steps of this theta. And now you're getting to Bayesian flow here, which is just this magical theta. And it's saying, okay, the Bayesian flow distribution, if you were to be able to get to that magical distribution in one step, one infinite step, that's kind of like taking a bunch of updates from step 0 with some schedule. Okay. And then what does that mean for the loss function? They're building towards something here. What are they building towards? Discrete time loss, continuous time loss, continuous data input distribution. Holy shit, dude. This is way too much math. We might have to skip and look at some of these figures instead. But let's get through some more of these. Given prior parameters theta and an accuracy schedule beta t, consider a sequence of n sender samples sampled at time 1 to n. Okay, so n sender samples sampled at time t1 to n. So you're receiving these samples of data, y, and you're doing this whole process n times, n total steps. So you have n total samples coming in at time tn. And because your time goes from 0 to 1, ti is just however many time steps you have. The sender distribution at step I is ps, where alpha I equals beta ti minus beta ti minus 1. Okay, this just kind of falls out from the fact that your beta of t is just here, dB dt is alpha t. So if that's true, then alpha I is just bti minus bti minus 1. The receiver distribution and the input parameter sequence is recursively calculated from this. Okay, so this is actually the loss function for the Bayesian update. To find the n-step discrete time loss, lnx, as the expected number of nats. Nats is like bits, but for a base e. So bits are base 2, nats are base e. Expected number of nats required to first transmit y1 to yn, and the reconstruction loss is the expected number of nats required to then transmit x. What? Using a bitback coding scheme, it requires DKL. So here's your KL divergence between your sender distribution and your receiver distribution. So that's what's going on here. KL sender receiver. To transmit a sample PS to a receiver PR. Okay, so your loss is just this KL divergence. but it's the sum of this KL divergence from I equals 1 to n, right? So for all the steps, and you're doing this for all theta or the expected value for these thetas, which are the parameters of your distribution, going from step 1 to n. My nose is like super itchy. Give me 1 second here. Yeah. All right. Your KL divergence is between your sender distribution and your receiver distribution. Your receiver distribution is specific, has specific theta, specific time, specific alpha. All of these are alpha's time dependent, and then theta is just based on your update. And then your sender distribution here does not have a time and does not have a theta, right? So your PS, which is the sender, is just coming from the data, which is sampled. So there's no time dependence there. That makes sense. And the P of all these thetas is this Bayesian update P, this Bayesian update probability distribution, which gives you theta at time step I, given the theta at the previous time step, some x and some alpha bar, or alpha I. Since the number of nats needed to transmit x using arithmetic coding scheme based on px is negative log px, and the marginal probability of theta n is given by pf conditioned on x comma 1. What the fuck is that? This is the reconstruction loss. The reconstruction loss is the minimizing the log likelihood, right? So we know that this here is the likelihood. P of x given theta is the likelihood. So here you have the log likelihood, and your loss is minimizing the log likelihood, or maximizing the log likelihood, or which is minimizing the negative log likelihood. Not directly optimized, however, it is indirectly trained by optimizing L and X, since both are minimized by matching the output distribution of the data. So even though you're not actually using this loss at all, by using this loss here, this KL divergence loss, they're saying you're effectively doing this. As long as B of 1 is high enough, the input distribution at t equals 1 will be very close to x, right? So at time t equals 1, that's at the very end of your optimization process, and hopefully by the time you get there, your input distribution will be the same as the output distribution, or will be very close to x, as in as close as possible to x, which is your actual data distribution. The loss function is defined as the total number of nats required to transmit the data, which is the sum of the nth step and the reconstruction losses. Okay, so the loss would be some combination of those two losses there. Lx can be derived as the loss function of a variational autoencoder. Variational autoencoder. Let's look at VAEs, you know? Let's look at some pictures. A variational autoencoder is whenever you have an encoder and a decoder like this, and you have some input, let's say this digit 4. You're feeding it into your encoder. You're getting this compressed low-dimensional representation of the input, right? An embedding, or a latent. That's coming into this decoder. Another way you could think of this is as a language between the encoder and the decoder. But that decoder is then reconstructing the original input, and you can then use a reconstruction loss. And over time, you'll basically get an encoder and a decoder that are learning how to basically compress this X. So what you've learned here is this encoder, which is a way to compress the data such that your reconstruction is as close as possible to the original one. Here you have a probabilistic encoder. I guess it's encoding it into the mean and the standard deviation. So something more akin to this is, I think, what they're going to show you here. Complete transformation defines the VAE as the loss function given by the negative variational lower bound, which is equal to this. So the KL divergence minus the log of x given y. I feel like I'm just getting lost here. I'm going to have to watch this again. Yeah. Here's what we're going to do. I think this is not productive here, right? We basically just have a bunch of explicit math, but like ultimately what they're getting at is that you're basically just doing this variational lower bound. You're using KL divergence. You're slowly over time matching this distribution here with the distribution here, right? So you're using your data to get better and better at estimating the output distribution of a true data set distribution. That's kind of fundamentally what's going on here. And they're getting needlessly intense here with these derivations. I just don't feel like I'm gaining anything by going deeper and deeper. N is fixed. Furthermore, discrete and discretized KL terms. For discrete and discretized data, KL terms do not have analytic solutions, leading to noisy gradient estimates. We derive a continuous function. Turns out to be mathematically simpler than the discrete time loss, as well as removing both gradients for the discrete and discretized KL terms, and needing to fix N. Okay, so N is the multi-specific number of steps for this training process. Eventually, they want N to go to infinity, right? They want it to be continuous. So here, they're going to go through all their bullshit, and they're going to finally get to a loss function that is continuous. So more bullshit, more bullshit, more bullshit. The limit, L infinity. So here you have the infinite time loss function. You have time is sampled from a uniform distribution in 0 and 1. You have PF. I don't know what PF is. Maybe P final distribution. What is F? I don't know what F is. PF, some distribution of theta given x, which is usually what we want to find here, right? Bayes theorem, P of theta given x. What is the probability of this model, these thetas being correct, given my x, my data, right? I want to find the best theta given my data x. So you have that, theta given x and t. You have your schedule. You have the expected value of p theta t. You have g of x, which we don't know what that is either. Where's g of x? Can I find g of x easily, quickly? No, I cannot. And then you have that squared over 2c, which we also don't know what c is. C is what? C over here? C, C, C. C is a scalar constant. Okay, good to know. But this seems a lot easier to me, right? And I think that's ultimately what they want, is they want this infinite time, continuous time loss to be easier and theoretically more beautiful than this discrete time one, which is up here, ln. So this is the discrete one, and what they're trying to get you to think is like, oh wow, look how gross this is, compared to, hey, look how pretty this is, right? But kind of the same variables are here, right? You have your alphas, you have your thetas, you have your t, you have your x. Those are the main things there. And if you scroll up here, what do we see? We see x, we see alpha, we see theta, we see t. So it's kind of the same shit in both of these. It's just that one of these is the KL divergence, which you can't really get. So you have to do this Monte Carlo, and you have to do it in step by step. And the fact that you have to do it step by step sucks. So now we're just going to do it all continuously, and we're going to get this. Okay. So we're just going to wave our hands and say that that's the magical answer. So let's say now you have a continuous data, still of dimensionality D. X is normalized. You have some input distribution for continuous data. It's a diagonal normal. What do they mean by that? They mean that you have a normal distribution, and you have a normal distribution in one dimension, but you can have a 2D Gaussian distribution, right? Here's a 2D Gaussian distribution. If you have a 2D Gaussian distribution, now this is the equation for a normal, right? But now you have this covariance. It's no longer just a simple little sigma. Now you have this matrix, right? So your matrix, you have sigma x, you have sigma y, you have the covariance between x and y. So it's a little bit more complicated. But at the end, it's the same thing. You have some mean and some variance. I don't know why they're using rho here instead of sigma. It's probably because they use sigma for something else. But here's your prior. So P of x given theta, your likelihood, sorry. So your likelihood is a normal distribution centered on x with some mu and some rho, and this is the column. So you're kind of assuming that the identity matrix here means you're assuming that it's independent, which maybe isn't necessarily a good assumption, to be honest. But it doesn't matter because over time you're going to get better and better guesses for this rho. We define the prior parameters as this. 0 is the length of D vectors of zeros. Input prior is a standard multivariate normal. So here's your input, your prior distribution. Your input is just, you're assuming it's a normal distribution that's centered on 0 with identity variance. Be to fit the prior mean and the variance to the training data. However, we found that the standard prior worked better, as well as simplifying the equations. It is important to remember that the distributions are never used directly to make predictions, but rather to inform the network's predictions. All that matters is that the parameters fed into the neural network accurately and accessibly encode the information received so far about X. And this is kind of where all of their assumptions kind of come to this crux, right? Where this entire, right, if intelligence is compression, and compression is you're trying to basically say, what is the simplest way to model my data set distribution, which is coming from the real world, right? There's kind of the fundamental assumption that's happening here is you're saying that the best way to encode all the data that I've already seen is in the parameters of a normal distribution, because I know that normal distributions happen all the time in nature. So that's kind of the fundamental insight here, and kind of I feel like all of Bayesian statistics is based on that. It's basically like assume everything is a Gaussian, and then now let's try to find the variance and the mean for that Gaussian, and then that seems like you're kind of making this big conjecture, but it actually works all the time. And that's why it works. Given a univariate Gaussian prior over some unknown data x, it can be shown that a Bayesian posterior, after observing a noisy sample y from a normal distribution with known precision alpha, is this. This is the actual Bayesian update. So A and B are your actual dimensions. So A, B, C. In this case, there's 3 dimensions. The distribution here is a categorical distribution with 3 categories. Here you have a univariate, one variable Gaussian prior. So it has one mean. It has one variance, rho alpha. And here they're saying, okay, well, here's a different Gaussian for a different B. This is for A, this is for B. And we're going to say, okay, if we want to update rho B and mu B, here's how we're going to do it in such a way that all we need to know is rho A and mu A. So you see that? Using the stuff that we know, right, the stuff that we were given, we can now update this other one. Both PI and PS or distributions are normal with diagonal covariance, which I don't like. I feel like that's a little sketch, right? Like this diagonal covariance, you're assuming they're independent when you do that, right? If you have covariances between y and x, if those are 0 and you have a diagonal matrix, what that means is that the variance in x is independent of the variance in y. It means you have two independent variables, but I feel like that's never the case in real systems. In real world, you never have diagonal covariance unless you're like flipping two coins or something like that. And even then, there's probably some weird relationship where, like, because you flip the first coin, your thumb is a little bit more tired and therefore the second coin flips differently. I'm here for sleep, but I'm more conscious now. Yeah, nothing like looking at math to slowly go to sleep. Maybe I do like a Bayesian paper reading where I kind of very slowly make my voice softer and softer and softer, and I make it like a sleep mix. You know? Hupo Stream Sleep ASMR. Can be applied by following Bayesian update. Okay. Finally, let's look at a picture, because, you know, I fucking, like, this math shit kind of puts me to sleep sometimes. Let's look at this Bayesian update for continuous data. Okay, so let's say you had univariate data, x 0.7. So there's only one variable here that you're trying to predict with a Gaussian, right? So you have some Gaussian here. Theta 0, that's your first guess. Theta 1 is your second guess. Theta 2 is your third guess. Theta 3 is your fourth guess, I guess, 0 indexed. So what we're seeing here is this first guess is just a Gaussian prior, this black line, and you can see how it's actually quite wide. And then you get your first measurement, which is this red X. So, okay, so first you're starting with, I'm going to guess that my variable is a normally distributed, centered on 0, and that's what I'm looking at here, right? I'm see this mu 0 equals 0, so it's centered on 0. And then you can see it's quite wide, right? Because I don't really know what the next thing I'm going to pick is. So then I pick one, and it's this red X, and I'm like, okay, well, if that's the value that I got, then I bet you the mean isn't here. The mean is probably somewhere here. So my new guess as to what this distribution is going to look like looks like this. It's going to look like this red Gaussian, right? So I've updated my parameters. Now my center is right here, and I'm a little bit more confident that the value is probably not going to be all the way over here, so I'm going to make my spread a little bit smaller, right? So you can see how this red one is a little bit more narrow, more peaky, more confident. And then let's say, okay, now the next sample I get is this blue one right here, this X right here. So I get this blue X. All right, well, shit, now I have this red X and I have this blue X. Well, shit, my initial guess of this mean is probably crap. Let me move it over here. So now my guess is here. So now I bet you that this variable, my guess for this univariate Gaussian is here. I have this mean here, and I'm a little bit more confident about the guess as well, so let me make it even more narrow. All right, so now this is my guess. And then you do the same thing for the 3, and you can see that now the 3, it moved it a little bit more this way, so you're like, oh, okay. Well, if I got this and then this and then this, I bet you it's even more likely to be within this range. So now my guess is this mu 3. So actually you can see how each successive guess decreases the variance, which doesn't necessarily need to happen, right? If I got a guess that was all the way out here, it would make the variance bigger. But you can see how over time, these parameters, right, theta, which is composed of, in the case for a normal distribution, is two parameters, mu and then rho, how you're updating them over time. You're updating theta 1, theta 2, theta 3, you're updating them. Theta 1 is mu 1 p1, theta 2 is mu 2 p2, or rho 2, and theta 3 is mu 3 rho 3. And these are your samples, y1, 2, 3. So y1, y2, y3 are drawn with accuracies 2, 4, and 6. So this is the alpha, right? So there's some schedule that's telling me, okay, each successive drawing that I'm doing, each successive sampling of these samples, right? These here, I'm going to assign them this higher alpha so that we get more and more close to what the true distribution is, right? We don't actually know what the true distribution is. All we can do is just get these samples from it and then slowly over time improve our guess as to the underlying Gaussian. Pretty good. You know, I actually kind of really like this figure. It's very easy to understand. Going BK2, your question, -y. Do folks watch well in part because you both asked that question about yourself and then work through the process, the subject matter in front of you and us? Going back to your question, I don't know why people watch, man. Sometimes I think that out of the people that are watching here, like 90% of them are fake. You know, so I wonder if Google wants to have people put shit on YouTube, right? Google wants more content on YouTube, not just because it brings more people to YouTube, but also because they want a huge video language speech data set to train vision models on. You know, so they want people to post things on YouTube so that they can get a bigger and bigger data set so that they can eventually train Palm version 7 and like a giant vision language model, right? So one way to do that would be to like, hey, anybody who's posting videos on YouTube, just rather than actually liking or giving them the number of views and likes and stream views and stuff like that is actually there, why don't let's just artificially inflate that, right? So that if we artificially inflate those numbers, then people are going to be more likely to produce more video, more content, which means that we get bigger and bigger data sets. You know, so I don't know. That's my secret conspiracy theory on, like, even though it says, what is it, something like 20 viewers right now, I bet you it's really only like 3 humans, and the rest of them are just basically juiced numbers made up by Google. Okay. I'm getting out of control. The Bayesian update distribution. You know what? I like this figure so much. Why don't we just go to the next figure? Let's just only do the figures here. Bayesian update distribution for continuous data. For x equals 0.7, the plot always shows the distribution p mu theta xy over input mean given initial parameters mu 0, rho 1, and... Okay, so similar thing here, except now we have different... This is the probability distribution for the mean itself given some initial parameters theta 0 and some x and some alpha. And they're showing you how the changes depending on the alpha, right? So here we were changing this normal distribution, right, which had some mean and some variance rho. And we saw how after we have more and more samples, we kind of we shift where our mean is and we change our variance and so on so that we kind of approximate better the distribution that is giving us these samples. But one thing that we didn't talk about is that we also have a way to kind of importance weight the samples, right? So if I was to say, okay, this sample is really, really important, these samples are not important, then the distribution would probably be more centered here, right? You would probably have the mean would be more over here because you're telling it this sample is much more important. So here what they're showing you is, okay, let's say we had some sample 0.7. If that sample had a very low alpha, right? If this alpha was 0.0007, you're telling me that this sample here is basically nonsense. You should just largely ignore it. And that's what we see here, right? So if this 0.7 is nonsense, then we're just going to stay right where we are, and we're going to say, yep, nope, I'm not going to really trust that sample at all. I'm going to sit right here with my mean 0 and my standard deviation, and I'm not going to adjust myself. But as we increase the alpha, then we're going to become more, we're going to start moving more and more, and you can see how the variance starts increasing, and then it starts moving the mean, and then it goes, and it goes right there. So in the extreme case, if alpha was 234, then as soon as you give us this x 0.7, we're like, you know what, this thing is so important, I'm so certain, I'm so confident that this x is the best possible x that I'm just going to immediately move there. Look at this, I'm just going to fucking throw myself over here. My mean is now exactly this value, and my variance is actually very narrow because not only am I confident that this is the new mean, but I'm also confident that every other number after this is going to be right on this number. So interesting how the choice of this alpha is going to change kind of how fast the parameters of that distribution adapt to this new sample. Video just pop out the third time. I'm just clicking in. Human here. I'm one of Tim's outliers. Reality is the tail risk. Human plus plus. Okay, so some of you are real. Or maybe you're just GPT or Bard pretending to be human. Okay, so we can see how this alpha is quite important. Let's go to the next figure. Bayesian flow for continuous data. So here we have a plot. We have a plot of time, t. So the x-axis is time. So 0 to 1 in time. And then we have a mean, which is 0, starts at 0. All the means start at 0. So all these lines are starting at 0. And I think this white is a trajectory, right? So we saw here an actual trajectory. Right, so here's the actual trajectory. It goes from mu1 to mu2 to mu3. So it goes 0 to 1 to 2 to 3 over some series of steps. Same thing here. So here's a different initial step depending on this alpha. But here we're seeing kind of almost like a top-down view, if you want to think of it that way. It's a top-down view of how the mean is changing as you go over time. And you can see how they're all kind of converging into this mean centered at x 0.8. So let's say that you had, I guess, one data point, which was 0.8, sigma 1 equals 0.2. So the standard deviation at time 1. So ultimately, you're trying to match a distribution, right? So you're saying, okay, what if the magical distribution that I was trying to match was centered on 0.8 and with a standard deviation of 0.02? So that's what I'm trying to get to. But I'm starting from a distribution that's centered on 0 with some standard deviation. The plot shows the stochastic parameter trajectory. Stochastic here just means random, right? Because there's a little bit of randomness. That's why it's a little fuzzy. But the trajectory, as in the path that mean is taken until eventually getting here, of the input distribution mean superimposed on the log scale heat map of the Bayesian flow distribution. So the Bayesian flow distribution says, okay, when you're here, so log scale heat map, you see how here it's red. So here, I bet you the red means basically 1. Like you're right on the money. This Bayesian flow distribution is telling you that your P of theta given x, right, which we know is P of theta given x, which is really what we want, which is the posterior, right? It's how good is our model theta? How good is our mean and variance that we're using given the x? If P of theta given x is really big, then what that's telling me is that this is a very good theta to explain our data x. If P of theta given x is very small, what that's telling us is that this is a garbage theta, it's shit, and it doesn't really work very well with this x. It doesn't explain this x very well. So if our Bayesian flow distribution is just P of theta given x at time t, right, then we're saying, okay, well here, it's all dark blue, it's all blue, so I don't really know. None of these thetas are necessarily good to model our x. But once you get here at time t equals 1, you're basically saying, look at this. This is red. That means that I know that right here, our theta is very, very, very good at predicting our x. Your theta sucks, bro. I identify as garbage theta. Right? So like really, ultimately, all of this is just trying to find the very good theta. Note how the trajectories all begin with mu0 equals 0 and fan out before converging on x. And this is really kind of what you want. What they're trying to show you here with this behavior is that you converge on the final solution, right? If you had one of these little lines that like kind of went out here and then it just kind of got lost and it went nowhere, that would be very bad news, because that tells you that you're not going to necessarily end up in the actual like with the actual answer that you want, right? That your optimization process might take little gradient steps, and it might move over here and it moves over here and it moves over here, and it ends up going in some weird direction, and it just ends up being trash. So the fact that all of these trajectories end up at the same place, which is your magical distribution that you really wanted, which is the data set, that's kind of what they're showing you here. It's like, hey, look at how nice this is. Look at the fact that our Bayesian flow distribution, if you just follow this Bayesian flow distribution, you will end up at the best guess. Okay, some more shit here. Output distribution. What do we got here? Input variance for Bayesian flow networks and diffusion models. Okay, so the input variance is the variance of the input. So I guess the more confident you are, the lower your variance is going to be, but it's at the very input, so you probably have to start with a pretty wide thing, right? Probably don't have a lot of confidence initially. So sigma 1 equals 0.001. So they're saying at the very end, at time equals 1, which is infinity, right? Then my variance, sigma, should basically be 0 or very close to 0 because I'm super confident. You see that? You see here how at the very end, your variance is basically should be tiny. But at the beginning, you kind of want a big variance, right? Because you don't really know what the fuck. You're going to get a bunch of samples, and those samples are going to kind of be all over the place, right? So kind of similar to what we saw here, right? Where the input variance, this black line, which is your initial estimate of the Gaussian, has a very wide, very spread out, very big variance. It's kind of annoying how like they use rho for variance here, and then they use sigma for variance here. Like I just find that kind of distressing. Is this optimization strategy usable on any network architecture? I guess. Yeah, you could probably do that. Right? All you're doing is just you're updating the parameters of a bunch of Gaussians that you're using to guess at the true distribution. But it's like I said, it's not that there's anything wrong with this. The problem is that doing this probably you're just going to waste a bunch more GPU compute doing that than just doing a transformer, and the transformer gets you there faster. So with a lot of these like fancy Bayesian flow networks or whatever the fuck, like variants of kind of, oh, we're going to do it this way. It's not that they're wrong and that there's some theoretical reason why it sucks or why this thing is better. It's actually very hard to say that one thing is better than another in theory, right? But a lot of times the reason these things never catch on is because actually running them on a GPU just isn't as good as a transformer, and people have spent so much time optimizing the transformer down into like these super nice CUDA kernels that basically do everything in one shot that like, dude, why are you going to be doing this? Why are you going to do these like Bayesian flow networks to get kind of a mediocre result? Okay, but let's actually see this thing here. Okay, so you have some input variance, and you have some gamma t. What is gamma t? Defined in equation 80. Output distribution. Following standard practice, this is equation 80. Gamma t is this, 1 minus sigma 1 2t. So your gamma t is basically just a function of your variance. Okay. Oh, actually here, your gamma t is just beta t over 1 plus beta t. So it's basically alpha t is the schedule. Alpha t is basically the confidence of your samples. Beta t is a function of alpha, and then gamma is a function of beta. So gamma is just beta, which is just alpha, which is just t. The blue line shows the variance gamma t 1 minus gamma t of the distribution over the input mean mu as a function of t. Okay, so the variance starts very low, and then it gets higher, and then it goes back down. Okay. Note that the variance at 0 is t equals 0 since the input prior is deterministic. What? The input prior is deterministic. What does that even mean? The input prior has some mean and some variance. It becomes small again as t approaches 1 and mu becomes increasingly concentrated around the data. Okay, that makes sense. The red and green lines show the equivalent network input variance for two different noise schedules from the literature, linear and cosine, during the reverse process of a diffusion model. Okay, so all of these are different schedules for the score that you're assigning to the data as it comes in, right? So we saw how this alpha ultimately is how confident are you in this data that's coming in. This data is coming in one piece at a time, right? You're getting this data one piece at a time, and you're updating your model based on the previous piece that came in. So we saw how if you have a very low alpha, very low confidence, you're not going to really care about those data points. And then as you get higher and higher alphas, it causes bigger and bigger changes to your parameters of the distributions that you're trying to eventually match to the data distribution. And here they're saying, okay, well, this alpha, which we're going to write an equation in terms of alpha that's beta, and then we're going to write an equation in terms of beta that's gamma, but ultimately it's basically just you're reordering the same shit as just this alpha. And here they're saying, okay, well, actually, this is what the diffusion or the noise schedule or the schedule for this alpha or the equivalent thing in a diffusion model looks like. So when you're doing a cosine schedule or a linear schedule inside a diffusion model, this is actually what you're doing. This is actually what it looks like. What you're really doing is you're saying, okay, well, the variance at time t equals 0 is 0, and then you're kind of slowly over time going down until 0. So what a Bayesian flow network does differently is that it starts down here and it says, okay, at the very beginning, I'm not going to trust anything. So the variance is going to be 0. I'm going to be quite certain that my initial guess is the best guess. And then I'm going to get a little bit more uncertain. I'm going to get a little wider. But then eventually, as I get more and more information, I'm going to make that narrower and narrower and narrower and narrow because I'm going to be more and more certain of that this is the exact Gaussian that I want. The input variance is much lower for Bayesian flow networks. Matthews Sousa, maybe not for transformers, but maybe an optimization over stable diffusion. Maybe. I'm sure you could probably have a fancy noise schedule that's based on Bayesian flow networks. If you can understand this math, you might be able to do that. Okay, so here we have a normal distribution parameterized by this gamma. Sender distribution. Sender, output, and receiver distributions for continuous data. So let's say you had, note that the sender and receiver have identical variance and the output distribution is the Dirac delta distribution. So if you remember, the Dirac delta distribution is a function whose value is 0 everywhere except at 0. So that's exactly what we're seeing here, right? This output distribution is the Dirac delta, and you see how it's just a perfect vertical line at 0, and the area under this line is 1. So don't worry about how that makes any sense, but through the magic of math, the area under this curve, which is a vertical line, is exactly 1, right? That's the integral over the entire real line is equal to 1. And then here you have two normal distributions that have the same variance, and they're saying these are the sender and the receiver. Okay, so your receiver, right, which is your initial guess, is starting at centered at 0 and with a unit variance, versus your sender, which is actually the little piece of data that you're getting. It's starting on the actual value of the little piece of data, which is x 0.7, right? So it's consistent with the previous figures. So now we can actually KL divergence between these two, the sender and the receiver, which is what's actually happening. Let's see. Let's go to the next picture. Output prediction, discrete time loss, continuous time loss, sample generation, discretized data. Data has been discretized into K-bin, so now we're moving from Gaussians into, okay, what do we got here? Output distribution for discretized data. For univariate data X, and previously we were looking at Gaussians, which can have any value, right? You could, if you sample from a Gaussian, it's not it's continuous. You can get any value here, right? You can get 0.00000001 and you can get negative 1.4573, whatever, up to infinity, right? Infinite resolution. But in most of the cases here, right, if we were doing token prediction language modeling, you're not going to output an infinite number, right? It's not going to be like something that has infinite precision. It's going to be a specific token. You're going to say the next token is A, the next token is B, the next token is A, right? There's like it's discrete. So here we have a univariate data X discretized into k equals 16 bins. The green line shows the continuous distribution. So the green line is our good old normal distribution, which has some mean around X and then some standard deviation sigma. So that's pretty standard, right? That looks fine. And that is discretized to yield the output distribution POX theta t. Okay, so now we have a distribution that's discretized. And why do we have this weirdness here, right? Like, what the fuck is happening here? So the reason we have this is because the area under this curve needs to be 1. It needs to equal to 1. When you sum all of the probabilities together, it needs to be 1, and that's what the area under the curve means. But if we can't have any of the probability mass that's underneath this shit here, which we cut out, that means we need to put it here, right? If I were to add up all these bars, they need to add up to 1. So that's why we're taking all the probability mass that was here and we're basically just adding it here, which is actually, this is one of the problems with, this happens in, when you're clipping distributions like this, you end up assigning more probability mass to the tails, and this ends up having all kinds of other problems, but I think that's probably not important for what they're trying to say here. Bin boundaries are marked with vertical gray lines. The heights of the green bars represent the probabilities assigned to the respective bins. Okay. For ease of visualization, these heights are rescaled relative to the probability density as indicated on the right axis. Okay. Note the clipping at plus minus 1. So here you're clipping. So you're basically saying you can't have a value here or you can't have a value here. So we're going to take all that probability mass and stuff it into this last one. It's added to the probability of the first bin. The area is added to the probability of the last bin. Okay. But this is kind of where it gets a little sketchy, right? Because does it still make sense to use a normal distribution like this for a discretized variable? I feel like this is probably not what you want. You probably want a uniform distribution. Let's see. More crap. Reconstruction loss. All right, here we go. Sender, output, and receiver distributions. Creative builds. Why not just average the mass across all k? Yeah, so what you're asking, averaging the mass across all k, is basically would be a uniform distribution, categorical uniform distribution. So this right here. But I don't know why not. I think we're going to figure that out here with this picture. Sender, output, and receiver distributions for discretized data. For data X discretized into 8 bins, the 3 plots depict the sender distribution, the discretized output distribution. Okay, so the sender is the red. So this is the data that you're getting. Whoa. You guys hear her? She's pissed. The output density is this green line. Okay. Output distribution is these buckets, these red bar or these green bars. Receiver distribution is this blue one. So the receiver is the guess, right? The sender is the true. So here's your true distribution, here's your guess. And the CTS, I think, is continuous and then continuous. Okay, so if you're getting this point and you have this importance on that point, KL equals 1 point. This is the KL divergence, and they're showing you how the KL divergence for the continuous case is higher than the discretized KL divergence, and that makes sense, right? KL divergence is a measure of the similarity of two distributions, right? How to measure closeless. Let me see if they have more here. KL divergence. KL divergence is always non-negative. KL divergence between two distributions P and Q is equal to 0 if and only P is the same as Q almost everywhere. So here, in the discretized case, you're actually getting more similarity from this discretized KL than you are from the continuous KL. So KL divergence is telling you that these green bars are closer to this red hump than this green hump is to the red hump. I can kind of see that, maybe. Receiver distributions for progressively increasing values of alpha. Okay, so the difference here, all these numbers are the same here. You have x 0.38, x 0.38, x 0.38. But the difference between this plot and this plot and this plot is this alpha. So alpha, which we know is kind of how important is that sample that you're pulling at the sample that you're getting. So alpha 20, alpha 120, and then alpha 500. Okay, so what is changing then? They're getting narrower. So as your alpha gets higher, you get narrower, which makes sense. You're more confident that that's the correct guess. And if you get narrower, when you discretize into bins, the actual spread starts to kind of impact how many bins you even have. Right, so here, you're so narrow that pretty much all of it is just in one bin. And that one bin has basically a probability of 1. Shown for the continuous distribution, dotted green line, which is discretized to create the output distribution and the continuous receiver distribution from section 4. Bin boundaries are marked with vertical gray lines. Note the KL divergences printed in the top right. Taking discretization into account leads to a lower KL due to the density bumps at the bin centers where X could be. Okay, so that's why the KL divergence is smaller and smaller and smaller, and the smaller the KL divergence, the closer the distribution is, the closer those two are, right? The guess, your guess, and then the true one. The advantage of discretization becomes more pronounced as the prediction gets closer to X and the more of the probability mass is corrected in the correct bin. Okay, so discretization leads to a lower KL divergence. And if a KL divergence is kind of your loss function, then I guess it gets you there faster. Still seems like it's not necessarily a good thing, right? Here, I'm looking at the continuous receiver distribution versus the receiver distribution. So I'm looking at this dotted blue line versus the blue line. Right, so the continuous is the dotted yellow line, sorry. So you can see how the continuous receiver distribution, you see how it's kind of just a normal Gaussian here, just looks normal and continuous, versus this receiver distribution that's here, it has these humps, right? Because as they said, the probability mass starts to accumulate on these density bumps, as they call it, on the bin centers. See that? How you're getting these bumps? And because you're getting those bumps, the KL divergence between this receiver distribution, this blue line, and this red line is lower. So this red line and this blue line here are less similar than this red line and this blue line here. See that? Continuous 1.35 here and continuous 1.81 here. Okay. Continuous time loss, pseudocode. Evaluating the discrete time loss. So this is a little pseudocode for how to get the continuous loss, discretized output distribution. Whoever implements this in PyTorch first wins. discrete data in which no meaningful order or distance exists between the classes, unlike the discretized continuous data. Okay, skip it. I'm sorry for you guys who came here for this math, but we're already at like 2.5 hours, so I gotta speed up. And I think in terms of bang for the buck, these figures is generally what you want to focus on. Accuracy schedule versus expected entropy for discrete data. So we know that the accuracy schedule is how important, the accuracy is how important is that alpha, right? And here they're calling it beta. Beta is just a function of alpha, which is a function of time. So all of those are kind of the same thing. But we have beta versus the expected entropy for the discrete data. Surface plot shows the parameter over parameter distribution p theta given x. So this is the actual thing, right? The thing that we want. This, how good is our theta given our x, p theta given x. P theta given x, and this accuracy schedule of the entropy of the categorical input distribution. So categorical input distribution, we're not talking about the continuous, we're talking about categories. P of x given theta for k equals 2 to 30. So k, I think, is the number of categories. So if you have a very small amount of categories, then what's this z-axis here? So the x-axis is your accuracy schedule. Your k is how many categories you have. And here they show just to 30, but like, for example, the amount of tokens, sentence piece tokenizer has about like 30K possible tokens, right? More than that. Vocabulary size of 267,000 different possible tokens. But I think 50,000 is more. Yeah, this seems a little bit outrageous. I think 30,000 is the number I had in my head, but imagine a k equals 500,000. This only goes up to k equals 30. So already right there, it's like, okay, well, what happens if we were to extend this plot to 50,000 categories k? I don't know, right? Would this have any meaning? The red and cyan lines highlight the entropy curves for 2 and 27 classes, the two values that occur in our experiments. The red and cyan stars show the corresponding values we choose for B1. Okay, so you have to pick the accuracy schedule, right? That's just like a hyperparameter, you're picking that. So they're saying, okay, we're picking this value for our example that has 5 categories, and we're picking this value for the example that has 30 categories. So we're picking a slightly smaller accuracy schedule for more categories. And if our accuracy schedule is really just these alphas, and those alphas, the bigger you make those alphas, the more confident you are about each individual thing. That means that the more categories you have, the lower you should make your accuracy schedule, which means that the less confident you should be about each individual piece of data that's coming in, which kind of makes sense, right? If you have, where's the actual definition of beta? Donde está beta? Right here. If your beta is just the integral of the alphas, and a low alpha means I'm not confident in this, and a high alpha means I am confident in this, then this makes sense. I don't know exactly why they would want to pick this one. Seems like you could kind of arbitrarily pick any of these. Here on the z-axis, we have the expected value of the theta given x, which is this, right? So the expected value of that for h. I think h might be, what is h? Entropy? H is usually entropy in physics, but expected entropy, yeah. So the expected value, expected entropy of the probability distribution of x given theta. So how good, how likely are these x given our model theta, right? That's why they call it the likelihood. It's how likely is it that we observe these x given we have some model parameterized by theta. That's the opposite with the posterior, which is how likely is it that this model parameterized by theta given that we have these variables, these data x that we've gotten. So here you're saying, okay, so you have the entropy of this, which is kind of loosely telling you how good is this fit. So why is it up high here? And what would this look like if we extended this up to 10,000 classes? Hard to say. All right, now we get to the actual thumbnail picture. Let's see if we can finally understand this. Bayesian flow for discrete data. Discrete, so we're still talking about categories. K equals 3, so 3 possible categories, right? So A, B, and C are the 3 corners of the triangle, right? 3 categories. A, B, and C. 3 corners of the triangle, and this here is, they call this the probability simplex. The input distribution parameters are theta 1, 2, and 3. Okay. Can be visualized as points on the 2 simplex with the data x corresponding to the bottom left corner. Okay. So x is the data that we received. So hopefully, if we get a data that tells us A, then we're going to move in that direction. So we start right in the middle, which is kind of like this. This is where we're starting. A, B, and C all equally likely. But then eventually we want to move to this all the probability only in A, which would be this corner here. So we can see how this Bayesian update distribution, this one here, the redness, right, which is telling you the high value of that Bayesian update distribution, which means that your theta is matching your x very good, right? And the Bayesian flow is just the Bayesian update with infinite amount of steps. That should be very high here where your x is, and then very low away from that. And we can see how we are updating. This is the Bayesian update distribution over time. You can see how the Bayesian update distribution gets closer and closer to the true x, which is your data set coming in. And then the trajectory of your thetas, which is coming from your Bayesian update, is slowly moving that way. And it seems very noisy, but it eventually gets to the right answer. See, look at that. It moves, and eventually starts chasing, and like a little mycelium strand in some kind of fungal growth on a petri dish, it moves towards the source of food. Single input parameter trajectory from theta 0 equals 1/3, 1/3, 1/3. So theta 0, 1/3, 1/3, 1/3. Right in the middle there is exactly this. 1/3 for all 3. Superimposed on log scale heat maps of the Bayesian flow distribution. And why is there different Bayesian flow distributions here? Why does the kind of rainbow background change? Because the Bayesian flow distribution here, theta given x, is also dependent on t. You see this? Look at this. This is dependent on t. So this Bayesian flow distribution changes. At time t equals 0, it looks different than at time t equals 2.27, at time 0.51, at time 0.63, and at time 1.0. So really, what you really want is the Bayesian flow distribution at time 1. That's the final answer. But you're getting to that. You're making guesses and moving in that direction from time t equals 0.02 to 1. Bayesian flow for binary data. For the input probability P1 of class 1, the plot shows several parameter trajectories starting from P1 equals 0.5 and t equals 0. So probability of class 1, so we have a binary data, which means that we only have 2 possible categories. This is like flipping a coin. And we start at, okay, we're flipping a coin. We're going to start from a uniform categorical distribution, which means P1 is 0.5 and P2 is 0.5. And here, eventually, it seems like all the trajectories are leading to this point here where P1 is 1. Note that both figured converge toward the data. So I guess you only have one piece of data, and the piece of data is that you got heads once. This is a fundamental consequence of discreteness, since all points in X are equidistant from input distribution. Let's keep going. We getting anywhere here? Page 39. So, okay, now we're starting to get to the experiment section. I'm going to try to make this under 3 hours, so. Like the boundary, you said the boundary gets added to the ends. Sorry, creative builds. I got focused and I missed your question. I no longer know what it's relevant to. But they're going to test these out, Bayesian flow networks, on MNIST and on CFAR. And then they're also going to do it on text8, which is 256 character sequences with 227 possible tokens. So even the quote-unquote language modeling that they do is extremely simplified, right? GPT and all these other models here, these are predicting the next sequence or the next token in a sequence, but the sequences are way longer, right? You're talking about potentially a context length of like 8,000, and the amount of possible categories or the amount of possible tokens is multiple orders of magnitude higher than that. So these are really bare bones examples in these experiments. The network was trained with continuous time loss, discrete time loss, blah, 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 used throughout MNIST, real and generated. Okay, so here they're generating MNIST. And I guess they kind of look the same, but, you know, MNIST isn't that hard, so that's not that impressive. Treating the grayscale pixel intensities as Bernoulli probabilities and sampling a particular binarization, which is held fixed. So a Bernoulli distribution is for a binary variable. Bernoulli distribution. Let's get a picture of this bad boy so you guys can see. A Bernoulli distribution is a discrete probability distribution that describes the probability of achieving a success or a failure, aka a two possible outcomes. So there's two classes. It's just two categories. Based on a unit, starting from the hyperparameters used in CFAR 10, we made the following modifications. The number of res blocks reduced, so they kind of take a unit and then grind it down. Optimizer was Atom W with a learning rate of 0.1. So this is the neural net that is predicting the values of the means and the variances, and I think the means are just going to be the values of the neurons. Total number of learnable parameters is 25 million. That seems a little bit more impressive. BFN is close to state-of-the-art with no data augmentation. Expected inverse relationship between the loss and the number of steps. So here, the no data augmentation. If you were to train a ConvNet to do this, you would probably have data augmentation, right? You'd be left, right, flipping it, maybe doing some adding noise to it, maybe cropping and rotating. There's all kinds of data augmentations you would do. So the fact that you get close to state-of-the-art with no data augmentation is impressive. So input distribution, output distribution. So here, right, the input and output distribution, these are the distributions that the network is creating, and you're getting better and better over time. So you can see how the distribution becomes closer and closer and closer to the real thing. For test set images, the figure shows the white pixel probability at 20 steps, evenly spaced between t equals 0 and t equals 1/3. Note how the input probabilities are uniform. So initially, it's equal probability to get either a 0 or a 1, which is black or white in MNIST, right? Predicts a superposition of multiple digits closely matching the per pixel marginal prior. So this is basically the average MNIST. Network learns the correct for the uniform prior and the input distribution, that the output distribution is much less noisy than the input distribution, that it changes more dramatically. as new information is received. This highlights the network's use of context to resolve ambiguity and noise in the input distribution. So the network is this part here, right? The network is using the input distribution to predict the output distribution. So the network is receiving the input, so it's receiving this, and then it's outputting this. And the input distribution is the result of this Bayesian update, where you're converging to that data point. Okay, so you can see how the data point was probably the number 2, right? And the number 1. So that's what was getting fed in right here, the number 2 and the number 1, right? And then that, over time, through this Bayesian update, you're getting closer and closer to that data set distribution. And then the output distribution is just, you're feeding that through the network, and it's telling you, okay, this is actually what it is. I guess that's kind of cool. It seems like it's a lot of effort just to get to here, though. MNIST losses against time. The left plot shows the mean over the test set of the continuous time loss used for the training for transmission time. This is a weird-ass loss function. You see, look at this. It goes very high, and then it goes down. So your loss increases and then goes down. That's not necessarily unusual. Sometimes the loss goes up for a little bit and then before it starts going down, but generally you want your loss to go down. Here you have cumulative continuous time loss, residual loss, and total loss. So the total loss is probably a sum of both of these. So the purple line is the addition of this green and this orange line. This looks more like a standard loss function here, this purple line. Which would be the total loss if the transmission process halted at t. Note the unevenness of L and the infinite loss against t. We speculate that rescaling beta to make the loss curve more uniform could improve performance. Okay. So this isn't necessarily good, you know? This means that you have to pick a beta kind of in a tricky way. What else do we have? Generated CFAR. Here generated, but you have a different number of bins. And you remember that by discretizing or the KL divergence with discrete versions of these senders and receivers, you got to a lower point. So I think that that's kind of what they're showing you here, is that this hyperparameter, which is how much are you discretizing. Samples generated using networks trained with discretized loss. The same random seed was used for both sets of samples. Note the improved image quality with 16 compared to 256 bins. This is kind of a weird result. You get better results. Is this better? I don't know. Does this grainy dog picture look better than this grainy dog picture? This is the problem with using CFAR. It's just like what the fuck am I looking at? Like, does this weird grainy car picture look better than this weird grainy car picture? Kind of, a little bit, maybe. It just looks flipped. Yeah. Right? Means of the input and output at steps evenly paced between 0 and 0.25. So this is equal probability of red, green, or blue. And you kind of diffuse out. CFAR losses against time. Holy shit, look at this loss function. Goes up, 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 and then down. Note the high loss, which we did not observe in the discrete data. It's got to be weird. And then they compare against some other stuff here. Diffusion models. Autoregressive baseline. Transformer. Gets a score of 1.23. BPC is bits per character over 1 million randomly cropped sequences. The reconstruction loss was 0.06. Text 8 dataset. Okay, so here you have text 8. Oh, you're like diffusing text. That's kind of cool. So similar to here, right, where because this Bayesian flow network is kind of like a diffusion process, right, you're kind of slowly removing the noise and getting a better estimate of the dataset distribution, right? And here you actually you kind of get that nice pretty picture where the noise kind of goes out. But this isn't limited to images, right? So you could just do this with text too. So here is text being diffused out. Here is on the x-axis here you have the actual sentence, right? So this is how it looks initially. It just looks like noise, except in this case it's a language noise, right? And then here's all the possible tokens. So in this simplified text 8 language modeling benchmark, there's only 26 or whatever this is, 28 possible tokens. So you can see how initially it's kind of like spread out over all of them. It thinks that there's a little bit higher probability of this than there is of this, but so on. Interesting how you notice how the letter E is a little bit lighter, and that's because in general, in most languages, the letter E is one of the most common letters. But then over time, you can see how here you have a little bit better guess, here you have a little bit better guess, and eventually look at this, you get the actual Philip Melanchthon in 5 steps heat copper etched map on a single cartouche. So now you've diffused out this text, and your probability distribution over every single token for each step in this sequence is basically collapsed into one. And like we know exactly this one. It's exactly this token for sure. Text input and output. So here's kind of a weirder visualization where they show you, rather than the probability distribution for every single token, they kind of change the size of the letter to show you how confident it is about that guess. So initially, you can see it's not very confident about anything. Mostly it just kind of thinks that the E is likely. So you see how the E is generally kind of the bigger letter here. But then as it gets, look at this one. This one, it is an E at the final, in the end, no, it's not. Look at this. So it's an E. It's a little bit more bigger E. I'm more confident. I'm pretty sure this is an E. I'm almost certain that this is an E. And then it's like, wait a second. This isn't an E. Oh, no. This is not an E at all. It's an S. And then it's like, okay, wait, S? Wait, no. Maybe it's still an E. No. It's an underscore. It's totally an underscore. Maybe it's still an E. No, it's not. It's an underscore. As you see how this E just keeps coming back? It wants it to be an E, but it's never an E. It just ends up being an underscore. It's a little story there. It's like literally that meme with the red button. You know, like the two choices and it's like sweating it. It's like one of them is E. It's interesting. But it kind of shows you that it's taking kind of a meandering path, right? The distribution over all possible categories in this categorical probability distribution that's trying to parameterize, it changes, and it thinks that it really wants it to be an E, but then it kind of goes back and forth and back and forth. It's not taking a direct path to the final answer, which is this here, which you should have a probability distribution that has infinite probability mass right here where the actual thing was, and then 0 everywhere else. I wonder if you do like 512 characters, then freeze the previous 512, and then update the next ground group, if there would be any benefits to the output text. Maybe, and that's kind of maybe the one thing that I feel like is a little sketchy here, is that it's hard to extrapolate, right? A lot of times the dynamics and the way that these things work at low data regimes are different than they work at medium data regimes and high data regimes. The way that these things work when your dimensionality is low is different than they work when the dimensionality is kind of medium and when the dimensionality is very high. So even though it's impressive that they can get state-of-the-art or close to state-of-the-art on these benchmarks like MNIST and CFAR, it's not necessarily indicative of what it would be like if you had a significantly larger data set, significantly more categories, right? What if you, instead of CFAR 10, which has 10 categories, what if you did this with ImageNet 1000, right? 1000 possible categories. Would it still work? How much slower would it be, right? You don't really understand those scaling laws until you actually do it. That's kind of part of the black box nature of machine learning and AI, is that the scaling laws are not theoretically derivable, right? You can't, it's very difficult to say what the behavior is going to be like 10 orders of magnitude in one way or another. So I don't know, that would be my main problem with this. But maybe one of you guys understands it better, you know? Having small categories but large context. Yeah. Okay. We're kind of getting on 3 hours, so I know we didn't read all the math. I know we kind of chickened out there, but I think we made a good effort try. Let me see if I can give you guys a little bit of a summary here. So this is Bayesian flow networks. We read this. This is a paper. The reason this paper is famous is because the Alex Graves guy is pretty famous. He's generally known for these kind of like weird, unique little like clever things like neural Turing machines and LSTMs and stuff like that. His LSTM was the first recurrent neural network to win pattern recognition. So he's someone who like understands this stuff deeply enough that he can kind of create new algorithms from the ground up. And here is his latest new algorithm from the ground up. And this new algorithm from the ground up is based on basically Bayesian statistics. And the kind of core idea behind Bayesian statistics is that the posterior, right? So let's say you have some data X, some data set X, a bunch of samples of data X, and then you have some model of that data parameterized by theta, right? You want to find the model that matches that data very, very well. And Bayes' theorem basically tells you, okay, well, however how good your model matches the data is how good the data matches the model times the probability of the model over the probability of the data, right? And as soon as you kind of write this equation, then you can go off into the horse race and be like, okay, well then now I'm going to substitute this equation here, and then I'm going to use a KL divergence, which measures the difference between these two distributions, and now that's going to allow me to create this evidence lower bound, and this evidence lower bound, I'm going to be able to maximize this and optimize this, and slowly over time get to guesses of theta that match this, right? That basically give me the best possible theta for a given x. So this is using that Bayesian statistics, Bayesian thinking to improve these distributions. And these distributions in this paper, there's basically two examples. He gives the example of categorical distributions, which are distributions like this, where you have a discrete set of possible values, and each of them has some probability. So those are the theta, the probability of each of those values, probability for each of those tokens. Or he says continuous variables, so a normal distribution that has a certain mean and a certain variance. So you have this input sender and this receiver. So basically the sender is the distribution of the actual data points. So actually, as you sample these data points out, you add a little bit of noise. That becomes like this is the distribution of what my data is, right? And ultimately, you want your model to be as close as possible to the actual distribution of nature, right? Like whatever natural process you're trying to create, whether that's the next token in a language or whether it's the pixel value in a picture, in an image, right? Like there's some actual true natural distribution to that. And all of this Bayesian updating, really what you're trying to get to is that true natural distribution, but you don't know what that is. And you get to it through these little messages, and those little messages are little data points. So you're saying, okay, well, I don't know what this distribution is. And then Alice, who is nature, is going to, here's one little message. And you're like, oh, okay, well, this kind of tells me something. Let me update my parameters. And you update your parameters. And then Alice says, okay, here you go. Here's another little data point. You're like, oh, okay. All right, let me update my parameters based on that one. And you're kind of iteratively improving your model over time based on these messages, which are just individual pieces of data that are being fed to you. They also introduce this term, where is it? Alpha. So this alpha term here is basically what they're calling the accuracy parameter, which is kind of like a noise schedule in a diffusion model. It's basically something that you're changing over the course of this optimization, and you're basically saying, okay, this alpha is a rough proxy of how good is that individual piece of data. So here you just have KL divergence, a bunch of math around showing that the KL divergence loss is going to get you to the right Bayesian update, which is going to get you to the right distribution. But I liked this figure. This is showing you kind of how, as you get more and more information from Alice, right, as each message comes, you get a better and better approximation of the parameters of the distribution that represents that variable. And here, this shows you how if you change the alpha, right, so if you have a very big alpha, you're going to be very confident about that particular piece of data, which means that you're going to kind of very quickly change your parameters. And here you can see how with a very high alpha, the normal distribution is right on top of that X and very narrow. Here's a fancy plot. I like this one, where basically there's this Bayesian flow distribution, which is this part here. It's the posterior, but also with respect to time, and you can see that as you get closer and closer to a time of 1, you kind of narrow in. It becomes more and more narrow, and it becomes more and more certain. And here you can see how your updates to the thetas, to the parameters of your distribution, which here is just your normal mean. You can see how basically they wander around a little bit. It's a stochastic optimization process, right? You're not getting to the final answer in one step. You're kind of taking these little steps, and sometimes the little steps lead you astray, but eventually you can see that all of these trajectories get you to the final answer that you wanted. Here they're showing you how the alpha parameter, which is kind of the noise schedule, actually you can compare it directly to the noise schedules that you have in your diffusion model. So this is a linear schedule, cosine schedule, and then the schedule that they use here for these Bayesian flow networks. What else? More crap. Then there's this whole part here that we kind of like glossed over, but basically you can discretize. When you discretize a continuous distribution, it ends up having some kind of relationship with the KL divergence, and a discretized KL divergence is lower than a non-discretized KL divergence, and I don't know, maybe that helps in some way or not, but it's probably has to do with this crap here where they're talking about the continuous time loss versus the discretized time loss. But yeah, that's basically this paper, and then they just go to show how you can use this to solve some simple problems. And here you have the path on a 3 simplex. So this is a probability simplex. It's just a fancy way of showing the probability of a token if there was only 3 possible tokens, and you can see the path it takes. But yeah, that's it, guys. I don't know, 3 hours in, do I fully understand this paper? No. Do I have some idea of kind of what they're doing? Kinda, yeah, I kind of see the rough ideas of what's going on. Maybe I don't fully understand the like theoretical guarantees, the theoretical reasons, like how this relates to a bunch of other things, but I can kind of see what this guy's putting up or putting down. I can pick up some of it. And hopefully you can too. Hopefully that was a little bit useful. But is the multimodality models using diffusion the first time? So you could have a multimodality Bayesian flow network, right? There's nothing that is saying that you can't have the input is whatever you want it to be. It can be tokens, it can be image. You could have a combination of images and tokens. So there's no restriction in terms of like the input modalities or the output modalities or anything like that. You could do this with pretty much anything. Thanks, Ed. Thanks. You're always super supportive. I appreciate it, But hopefully that was interesting. If you guys ever discover any more interesting learnings from this, or if you come to any better compressions of the knowledge in this paper than I came to, definitely let me know. Drop by our Discord channel and let us know what you've discovered. With that, though, thanks, Luke. Thanks, John. Thanks, John Ryan and John Egan. Thanks, War. Thanks, Azur. Thanks, Matthew, Navjot. Chinese name I can't read. Chris, Riddell, Mateus, Matt, Roman again, especially because you donated some money to the GPU fund. Creative Builds, Yujun Liu, everybody. Thanks, y'all. You guys have a great weekend. See you guys later.